आप हेलो हेलो ओके हेलो 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 वస్తుందా हेलो
Hello. Hello. I give a shout. But he's saying hello.
हेलो
Hello. Hello.
हेलो 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 हेलो
Hello. Hello.
हेलो हेलो দিয়েছেন? হ্যালো হ্যালো ওকে హలో 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 వస్తుందా హలో
Hello. 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 I cannot shout. But he's saying that it will be captured. Is it coming? Hello.
హలో
Hello. Hello. Start.
హలో 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 హలో
Hello. Hello.
హలో 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 హలో
నేను కొంచెం పెంచుతాను మీరు అక్కడికి వెళ్ళి
ఏదైనా ఉంటాయి కదా హలో 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 Hello. Hello. Good morning, everyone. Good morning.
Now, do I have to shout? Hi, welcome to IIPE. Welcome to IIPE. For 1 minute. Welcome to IIPE. We have. Are you captured? Okay. Welcome to the Indian Institute of Petroleum. Okay, so hello. But can the audience hear me? Okay. Okay, so I have to just keep it closer. Do I have to shout? Hi, welcome to IIPE. Welcome to IIPE. For 1 minute. Welcome to IIPE. We have. Are you capturing? Okay, welcome to the Indian Institute of Petroleum. Okay, so come. But can the audience hear me? Okay. Okay, so I have to just keep it closer. Good morning, everyone. On behalf of the Indian Institute of Petroleum and Energy, I extend a very warm welcome to each one of you to the inaugural event of GIAN course on Next Generation Composite Membranes for Hydrogen Energy and Environmental Application. We have with us today our guest, Professor V. Vedanpur, Foreign Faculty for the GIAN course on NGCM, Professor Vijay Kumar, Dean of Research and Development, IIP, Professor T. Hemant Kumar, Acting HOD, Department of Chemical Engineering, and Professor Raka Montal, Assistant Professor, Department of Chemical Engineering, and the local coordinator of GIAN IIP. A hearty welcome to you, professors. We'll now begin the event with a lamp lighting ceremony. May I now request all the guests to kindly proceed to the stage and light the ceremonial lamp to officially inaugurate the event. Can I please request all the participants to stand? Well, thank you for the meaningful gesture. We'll now present a virtual tour of our institution, IIP Vishakhapatnam. This video will offer you a glimpse into its vision, state-of-the-art facilities, and the vibrant community of IIP.
to meet the global energy and climate challenges by providing the punchable solutions espoused by our Honorable Prime Minister. IIPE seeks to turn India into a global energy hub. The Global Industrial Advisory Board of IIPE helps align the Institute's research initiatives with technological innovations. The thrust areas of IIPE's research are biofuels, batteries, carbon capture and sequestration, hydrogen production and storage, capture and conversion of CO2 into green fuels or EOR, renewable energy, waste to energy, and geothermal energy, among others. With industry partners, HTCL, NGCM, SBI Foundation, ONGC, IOCL, OIM, GAIN, Halliburton, and Greenco. The research activities help meet real-world needs of achieving a net zero goal and contribute significantly towards the United Nations Sustainable Development Goals of ensuring access to affordable, reliable, and sustainable modern-day energy for all. IIPE is executing a project in collaboration with NTPC to develop a one-ton per day plant worth rupees 35 crores for hydrogen generation from seawater. This will fulfill the dream of Visakhapatnam becoming the first hydrogen city in India. The academic program of the Institute is aligned with NEP 2020, offering BTech, MTech, MSc, and PhD programs. The Institute enriches itself with an international academic board for framing the course structure. Some of the innovative academic initiatives are Sandwich PhD program, hosting foreign researchers, international electives, global students internship program, joint MBA with IIM Visakhapatnam, BTech MS program with US universities, and industry-sponsored master's programs in energy science and engineering program. Joint representation in challenge education. BTech provides fellowships to undergraduate industry-sponsored master's programs in energy science and engineering, social and economic representation in challenge education. BTech provides fellowships to undergraduate energy science also social and economic representation and sustainable solutions.
It's my pleasure to invite Dr. Raka Muntal to officially open today's proceedings and give a brief overview of the GIAN course on NGCM. It's my pleasure to invite Dr. Raka Muntal
Thank you,
to
Professor
officially
Elizabeth.
open today's proceedings and give
So
a
on
brief
behalf of the
overview
organizing committee,
GIAN course on
I am so
NGCM.
happy to welcome all of you to today's program.
So I take this opportunity to introduce about the GIAN program to all of you. So GIAN program is basically an initiative by Ministry of Education. It was initially started in 2015. So I take this opportunity to introduce about the GIAN program. There was a short course is basically an initiative by Ministry of Education. It was after that the fourth round so I take so after started and we are currently going to the fourth phase and course is so that is going for Ministry of Education. So this course is a part of after that so the GIAN or the full started GIAN is actually the global initiative of academic leaders. It is a program of Ministry of Education by Government of India. It is designed to tap the talent pool of scientists and entrepreneurs is actually internationally to encourage their engagement with the institutes of Ministry of Education by Government of India in India so as to augment the country's existing scientific resources, accelerate the pace of quality to encourage their engagement in scientific and technological innovation of global India in India so as to augment the country's existing scientific resources, accelerate the pace of quality and encourage their engagement in scientific and technological innovation. This institute is the national coordinator of GIAN currently. So, existing base of the director says that ancient India GIAN was regarded as the highest form of scientific research. Continuing this rich tradition, the global initiative of academic research currently is an initiative by government. It enables institutes of higher education in India and it invites the experts of international continuing this rich tradition, the global initiative of academic research currently is an initiative by government. It enables institutes of higher education in India and it invites the experts of international continuing this rich tradition, the global initiative of academic research currently is an initiative by government. It basically centered about the brain. Its application for enhancing the purpose like water purification, gas starvation, and washing for higher research. So it is scheduled from Monday to evening. Basically centered around the brain. Our enhancing the professor's letter code has so we are honored and washing for higher research. Today, so we is a from Monday to evening. Basically centered around the brain and university. Our professor's letter high has published research journal and washing for higher research. So we is a mixer from Monday to evening. Basically centered around the brain and university. Our professor's letter high has published research journal. We have planned some tutorial activities also. Sir, I have shared the schedules follow so we can go through that schedule and see that particular channel is for energy and what time. This is some of tutorial activities participation and I am so glad to see that there is a huge response from all over India and I can see channel participants not only from Delhi but also from extreme southern part of India and also from registered from Mumbai also participants all over India and I am so happy and see that there is not only from Delhi but also from extreme southern part of India and also from present students. So I thank all of you for joining us and I am so happy and see that there is not only from Delhi but also from extreme southern part of India and also from
May I now request Dr. D. Hemant Kumar to highlight the departmental activities of chemical engineering. Thank you, ma'am. May I now request Dr. D. Hemant Kumar to highlight the departmental activities of
Good morning,
chemical
everyone.
engineering.
Very well warm welcome to this GIAN course. I take this opportunity to congratulate Professor Raka to
May I now
get this
request Dr.
GIAN course approved from the GIAN accreditation, and we have made a GIAN course also approved in this call for the series carbon capture course. And I take this opportunity to get this GIAN course approved activities that are currently going in accreditation, and we have made a GIAN course. So department currently has 10 faculty members with interest areas of the series carbon capture modeling, control, and water treatment, membranes, hydrogen generation, and storage. And we also work on carbon capture and sequestration. Faculty members with these areas, our department is writing a lot of proposals to the both governments, hydrogen generation organizations. We have currently, and we also work on carbon capture. 5 projects that are running with the help of NTPC. We are doing some corrosion modeling. 2 projects as proposals to the both governments. We have got one project from Solar Collaboration of India Limited on application of solution for renewable energy systems. We are doing some corrosion modeling. So we have as a department we are doing strong, and we are focusing on major both renewable and energy sector. And student strength is also increasing, and we are saying as a department we are doing strong. I wish all the best for this course on major both renewable and energy sector. And student strength is also increasing, and we are saying as a department we are doing strong. I wish all the best for this course on major both renewable and energy sector. Student strength is also increasing, and we are saying as a department we are doing strong. I wish all the best for this course on major both renewable and energy sector.
In a similar way, we are kind of focusing on institutes represented energy into what we call as in a similar way, we are kind of so these are the ones which are represented energy into what we call as all this is probably the 30-second workshop conference that is as you know, gas behavior progress, but in such a but all these gas progress, but finally taken so in that but all these gas finally somebody in that participate summer break and we have interest for the students from the local schools which are not kind of endowed with these kind of facilities, so they come to IIT IIPE and spend a couple of weeks, and they get connected to the faculty and see what are the developments have been happening in science and technology. And we have a program for college teachers, local college teachers, so they can come and collaborate so that they can apply the scientific projects to the funding agencies in collaboration of the faculties. So, and recently we have also initiated the global internship program. So coming this July of 2025, we will be hosting the first 2 global interns fully funded by IIPE. So, and we have our own funded PhD program. And again, from July 2025, we are starting our own postdoctoral fellowship program. So Institute will be giving the postdoctoral fellowship. So it's all the, whatever the progress that we have been making in the science and technology, we want to take it to the people. So in that scenario, I think GIAN course is one of the best opportunity that we have to get connected to different students, different participants throughout India. And I am sure that at the end of this 6-day program on 8th, so everyone will be extremely enlightened in the particular topic of membrane technology, how it can be utilized in the hydrogen and environmental. Thanks a lot.
Thank you, sir. Our distinguished guest for the event is Dr. Wahid Vedanpur. Dr. Vedanpur is a renowned professor of environmental engineering from Istanbul Technical University. He is also working as a professor of applied chemistry in Kazami University, Iran. His research interests are focused on membrane science and technology for water and wastewater treatment, especially fabrication of anti-fouling polymeric membranes. He has published over 300 papers in internationally reputed journals and handled many number of internationally reputed research projects in lab scale and industrial scale. It's my privilege to request Professor V. Vedanpur to deliver today's address.
Hello. I would like to thank the Andhra University and Indian Institute of Petroleum and Energy for hosting me, and especially Professor Raka for their hospitality. I am glad that I am in your meeting. I am from Iran, and my nationality is Iranian, but now I am adjunct professor in Istanbul Technical University for 5 years, and we research in membrane filtration and separation, both for water treatment and wastewater, and also in gas separation. I have completed more than 20 projects in industrial scale. For example, we have a production of reverse osmosis membrane in Iran in industrial scale. Our separation of carbon dioxide from flue gases. Now I have some projects from Horizon, from Europe, that focus on separation of gases by ceramic membranes. I have a project about production of membranes for fuel cells, for instead of naphthalene, with sulfonated polyether sulfone and polysulfones. And mostly my research area for publishing the papers is fabrication of membranes. We use the new materials, new monomers, new polymers, new solvents, especially green solvents, green biopolymers, novel nanomaterials for fabrication, and the main aim of our research team is reducing the membrane fouling, because the main problems in membrane is fouling during the time, and we try to reduce the membrane fouling, for example, with increasing hydrophilicity, with change of the main polymer for increasing durability, stability, increasing chemical resistance, and others. I hope we have good course in these 5 days, and we have a happy and scientific days. Thank you.
Thank you, sir. May I now request Professor Vijay Kumar to kindly come forward and felicitate Professor Vedan Paul. We will now be playing the national anthem. I request everyone to rise as an anthem is played. I'd like to invite everyone for a group photograph to mark this occasion. All the participants can now proceed to 31240.
I will try to introduce the membrane and say what is the membrane and why we want to use the membrane instead of traditional methods, and what is the mechanism of separation in membranes, and we will define the usual words that are used in membranes, such as what is rejection, flux, recovery, and others. The first definition is what is a membrane. We usually say that a membrane is a semi-permeable physical layer. A semi-permeable physical layer. That means membranes allow some materials, some species, some molecules, or some ions can pass, and others cannot pass. Okay? And this is a definition, a simple definition that we have a barrier, and this barrier mostly is a porous layer, porous barrier. But we have non-porous membranes also. But most of the membranes is porous, and we can say that a membrane is similar to filters, but different from filters. In filters, we only separate solids from fluids. We separate particles from air. We separate particles, microorganisms from the water with filters. Okay? The fluid, the gas, the liquid pass from the filter, and the solids do not pass. But in membranes, we can separate dissolved ions, dissolved molecules in liquid that filters cannot. The difference between filter and membrane is that the membrane can separate dissolved ions, dissolved molecules from the fluids. But in filter, we have only separate particles. Therefore, the pores of the membranes should be very small than the filters. Usually, the filters have 200, 300 nanometers in pores. But most of membranes have pore size less than 100 nanometers. Okay, therefore we can say a membrane is a nanotechnology because we can produce pores in nanometric scale. This is a simple picture of the membrane. You see that the small molecules can pass and the big molecules cannot pass. But this separation in most cases is not complete. It's not complete. We have not complete separation of a species. We have rejection, for example, 98%. That means some molecules cannot pass and some solvents or some ions, some molecules can pass. And therefore, the selection, the selectivity is not infinite. We have a restricted separation because the pore size of membranes usually is not uniform. We have not uniform size of the pores. When we say these membranes have, for example, 20 nanometer pore size, this reported data is average data. We maybe have 15 nanometers or 30 nanometers. Therefore, we have not the equal and similar pore size, and therefore, when we have a non-linear pore size, therefore, we have not complete separation. The second question is that why membrane separation is important, especially in recent years. Because the main reason is that low cost or low energy consumption. The membrane separation is a physical separation in most cases. We have also some chemical separation, such as liquid membranes. But in the most cases, we have a physical separation and no need to any phase separation in liquid or gas. For example, in distillation, we must boil the water for boiling and transfer from liquid phase to the gas phase for separation. And this phase change needs very high energy. But in membrane, we have not phase change. In separation, we have a liquid, for example, in reverse osmosis, with using this barrier, the water pass from the membrane and the solutes, the ions, the salts cannot pass. And we only apply pressure. And for this applying pressure, we use pump. And the pump use energy. But the use of energy in pumping is very, very low from the boiling. And therefore, reverse osmosis now substituted with thermal processes. And the most application of RO membranes is desalination. Other reason is that flexibility in designing. The membranes needs a very low space, and we can compact the models, pressure vessels, in a very low space. We can put the membranes to the high or to the right and left, vertical or horizontal. Right? We can change the designing. But in distillation, for example, we must prepare a very tall column, and we cannot fabricate the column as a vertical or horizontal. Okay? Therefore, the membrane design is flexible. In membrane separation, we usually have no dangerous waste. In membrane, we have a permeate and we have a concentrate. This concentrate is problem in membrane process, but no produce new waste, new dangerous waste, or no use dangerous and toxic chemicals. For example, in absorption column, we use amine solutions for absorption of carbon dioxide. This amine solution can lead to the weather and is dangerous. But in membrane processes, we have not dangerous additive or dangerous gases, and therefore, generally, the membrane process is environmental friendly. And we have no risk and hazards, very low risk. We usually use the pressure of 2 atmosphere, or in RO, we use 50 atmosphere pressure. And this pressure is not important. For example, in production of polyethylene from ethylene, we have a 700 atmosphere pressure. And 50 atmosphere pressure is very low in industry. And we have no risk about the destroying of the equipment and other problems. Therefore, the membrane process is an economical, environmental friendly, and low risk process. I say the advantages of the membrane processes, but we have some drawbacks and disadvantages. The main disadvantages of the membrane is fouling. Fouling means that the productivity of the membrane reduces during the time. The flux reduces or the rejection is reduced. The selectivity is reduced. In the first day, we have a high flux, and after 2 months, due to the plugging of the pores, due to the layering of a foulant layer on the membrane surface, and other reasons, the flux reduces, the selectivity reduces, and after 1 year, 2 years, based on the membrane, we must change the membrane. Or for reducing the fouling, we must wash the membranes. For example, in dairy industry, we wash every day the membranes because the protein of milks can attach to the membrane surface and causing to fouling. But in reverse osmosis membranes, we usually every 3 months we wash the membranes. Okay, related to the membrane process, the cleaning and washing is different. But cleaning and washing need to money and cost, need to the washing agent, need to the labors for these works. The second problems in membranes is low selectivity and flux. As I say, that the separation of membrane usually is not complete, and we have 90% rejection, but some processes usually, for example, distillation, usually have complete separation. And we try to increase the selectivity and the rejection of the membranes. And another problems is the high capital cost. We say that the energy consumption of membrane is low, but first capital cost is high because membranes is high technology. But during 20 years, the price of membrane is reduced. For example, 30 years ago, 8-inch RO membranes had $1,500, but now reduced to $700, half of the 30 years, because when the RO membranes is used mostly, the production increases and the cost reduces. Therefore, we have a high capital cost, but this capital cost reduces, and in the future, we have not this problem. Membrane is a separation process. We want to separate two species from together. Therefore, wherever separation is required, membrane can be used, but if it is economically viable. If we see that the membrane have economical viables, we can use the membranes. Almost in all separation process, we can use the membranes. And we have almost 20 different membrane processes, and we can separate gases, liquids, organic solvents from their purity. And therefore, you see in most of the technology and factory, we can use the membranes for separation of some impurities from the air, from the gas, from the soil, from the water, and medicinal, breeding, agriculture, and others. Therefore, the membrane scientists first check the economical viability, and the second is fouling problem. Maybe one process can be instituted with the membrane, but the membrane will destroy during 1 week. Membrane can be separate, but have not durability, chemical durability, solvent durability, thermal durability. Check these conditions. If the membrane can be used for a long time, membrane can be used instead of a traditional process. About membrane materials, we can say that all materials can be used for the membrane fabrication. Polymeric, organic materials, inorganic or ceramic materials, metal or liquid. We have all liquid, solid, metal, non-metal, inorganic, ceramic, and polymers. The usual polymers used in fabrication of the membranes is polysulfone, polyethersulfone, cellulose acetate, regenerated polyamide, and generally, membrane can be made from all of the polymers, polyethylene, polystyrene, biopolymers, chitosan, polylactic acid, and every polymer. We can increase the stability of membranes, polymeric membranes, with cross-linking. When we have a polymer is not suitable for membrane fabrication, we can change the properties of polymers. For example, with sulfonation, with carboxylation, with amination, with cross-linking, or addition of other additives, or blending of a polymer with other polymers. Therefore, you can find in literature that every polymer have been used in membrane fabrication, but the mostly used polymers are these polymers. A good polymer should have good flexibility. The flexibility and durability of the membrane is important. Membrane is a thin layer. The thickness of membranes is about 100 micrometers, usually, and very thin. But if the polymer is brittle, we cannot apply pressure. We cannot use the brittle polymer in membrane fabrication, and we usually use amorph polymers in membrane fabrication, amorph, not crystalline. The crystalline polymers is brittle, and we cannot use, and the molecular weight of the polymers should be high. In some research, one researcher told me that I have now synthesized a novel polymer, and you can prepare a membrane. I asked him the molecular weight, and he said that the molecular weight is 5,000 grams per mole. This 5,000 is not good for membrane fabrication, and when we fabricate a membrane, we see that the membrane is brittle. and we need to high molecular weight for flexibility and chemical resistance. And the polymers in most fabrication process need to dissolve in solvent. We must first dissolve the polymers in good solvents and next prepare the membranes. And in most cases, the synthesized polymers have not good solubility and we cannot use them. Therefore, we must change the properties of polymers to good processability and dissolving. We have ceramic membranes that usually fabricated from alumina. The ceramic membranes is expensive than polymeric membrane because the use of materials is high and the need for high temperature for fabrication. For example, when we use the alumina for fabrication of membranes, we need 1,700 centigrade temperature for 6 hours, 8 hours for sintering of these materials, and this causes the high cost. And the fouling of ceramic membranes is lower than the polymeric. The durability, chemical resistance, solvent resistance, thermal resistance of the ceramic membranes is better than polymeric membrane, but ceramic membrane is not flexible and is brittle. When we want to use with a little small touch, can be destroyed, can be brittle, and we cannot use them, but the fouling in ceramic membrane is very low. In daily industry, usually use ceramic membranes. When we have a hot stream, hot gas, hot water, we use ceramic membranes because the polymeric membranes is destroyed in high temperature. Usually the polymeric membranes used in lower 50 centigrade temperature. But ceramic membranes can be used to 100, 300 centigrades. Metal membranes mostly used for hydrogen separation that Professor Raka will speak about. But we can fabricate porous metal also. We can porous metal membranes that we can use as a microfiltration and ultrafiltration, but they are very, very expensive and used in nuclear processes for separation of some pollutants. And we have a liquid membranes that in liquid membranes, we usually have a support that the liquid is supported. And the main separation agent that we say carrier membrane is liquid phase. We have in most cases solid substrates, solid support. But their only support and the main separation layer is liquid that we will discuss next. In this slide, we define the most used words and terms in membrane process. We have a permeate. Permeate is the part of feed stream that passes from the membrane. If this is membrane, this solutes is permeate. The permeate is the feed stream that passes from the membrane, and for showing the selectivity and the rejection, we usually measure the concentration of the special solute, special ion, in permeate and feed, and compare it for saying that the rejection. With measuring of the, for example, A component in permeate and the first concentration in the feed, we can say that how many of the molecules or ions are rejected. Reject, that means not pass from the membrane. Rejected solution and rejected ions or molecules. Therefore, we need to measure the concentration of the solutes. In the lab scale experiments, for example, in your thesis, the measurement of this concentration is problematic. Maybe we need HPLC, GC, UV spectrophotometer, and other techniques for measuring, and true measuring is important. Analytical chemistry is important in this case. When we have a range analysis of concentration, our rejection will be wrong. Therefore, in lab scale, we need to high technology for measuring of the concentration. For passing of the permeate from the membrane, we need driving force, a force that pulls the solids from past the membranes. We generally have 4 driving force: difference in concentration, difference in pressure, difference in temperature, and difference in electro potential. Difference in pressure, that means we must have high pressure in the feed side than the permeate side. Usually in microfiltration, ultrafiltration, nanofiltration, the permeate size is wetter and the pressure is 1 atmosphere. But we apply 2, 3, 4, 5 atmosphere in the feed side that is higher than the permeate side, and this delta P causing to the passing of the permeate from the membrane. Or from the delta C, we must have a difference in concentration for diffusion of the solutes from the membrane. Therefore, we have a transmembrane pressure, that means delta P. For saying how amount the permeate is past the membrane, we have flux, that flux with a unit of kilogram per meter hour or liter, is the amount of the current penetrated, percolated, or passed from the membrane per unit time and per surface area of the membrane. With a high membrane surface or high time, we will have a high flux. We have also permeability. Permeability in gas separation and water separation is different. I will define permeability in gas separation, but in permeability in the water, in liquid separation, is the pressure, is the ratio of the membrane flux to applied pressure. We divide the flux to the applied pressure, and this is the permeability. Permeability is flux per delta P. This is in liquid separation. In gas separation, the definition of permeability is different, and I will speak later. Another definition is recovery. The Membrane separation is a mass transfer mechanism, and we can write mass balance for the feed and permeate. When we write the mass balance, we say that the flux or flow of the feed equal to the flow of permeate and flow of concentrate. In most cases, when we test the membranes as a cross flow test, that's UF, RO, and F, some gas separations, is the cross flow test. We have a feed stream that comes to the membrane surface and divide two phases. One phase is the permeate that pass from the membrane, and the second stream is concentrate or retentate or rejected stream. We have a one entrance divided to two streams. One stream is permeate and one stream is concentrate. Related to the membrane process, the main product can be permeate or can be concentrate. For example, in reverse osmosis, our product is permeate. We want to desalinate the water and produce desalinated water. Therefore, permeate is our product. But in a UF process, in most cases, our product is concentrate. We want to separate water from a solution and concentrate it for concentration of milk. We want to reduce the water of milk. Concentration of dye. We want to concentrate the textile dye for reuse in dyeing. Therefore, related to the membrane process, the main product can be concentrate or permeate. About the mass balance, we say that mass is not destroyed. Okay? When we have, for example, 100 kilogram feed, the sum of the permeate and concentrate should be 100 kilogram. And we can write partial mass transfer. I define the rejection that show the ability of separation. But we have a recovery. What is recovery? Recovery is meaning that how many amounts of the feed result our product. In this case, you see, we usually, the permeate is our product. The amount of our product, that means permeate, per amount of the feed. For example, we have 100 kilogram feed, and this changes to 70 kilogram of our product. Our recovery is 70%. Okay? Understand? The recovery is meaning that how many we have useful product per the first feed amount. The high recovery is good because we will have the high product. Okay? But in membrane process, we cannot reach to complete recovery. We cannot reach to complete recovery because the complete recovery means that all of the solvent should be separated from the solute. And when we have a high concentration of solutes on the membrane surface, causing to the high fouling. We can separate all of the solvents from the liquid. But when we have separate all of the solvents, a layer will be covered the membrane surface and block all the surface, and the membrane will be destroyed. Therefore, we have not complete recovery. Based on the process, we have usually 70-75% of recovery. Sometimes we can increase to the 90% based on the feed concentration. If the solute concentration is low, we can increase the recovery ratio. Therefore, recovery shows that how many products can be produced. For example, in the commercial modules or modules, after preparation of membrane, we change the membrane to the module form. What we say in India, module or module? Module or module? Module? Okay. In the module, we change the membranes to module. In the module, we increase the area to volume of the membranes for industrial application. This is a catalog of the commercial film tech, and you see that the recovery of a module with 1 meter length is only 50%. That means if we want to reach to, for example, 75%, we must use 5 series modules to reach the 75 recovery. Therefore, with 1 module, we can only reach to 10 or 15 recovery. And for increasing of the recovery, we must use the series modules in a pressure vessel. Therefore, in industrial pressure vessels, we usually use 4, 5, or 6 modules in series that the concentrate of 1 modules go to the second go third, and parallel goes. In industrial modules, usually say the flux with GPD or GFD, that is gallon per foot square day or gallon per day. GPD is flow, GFD is flux. GPD is flow, no area, you see no area, but GFD is flux that have area of the membrane used. From a theoretical view, the flux in the filtration membranes, that driving force is delta P, can define as this mathematic. The delta P is the top, is the above, and the viscosity and the resistance in the bottom. You see that when we increase the pressure, the flux, the permeability will be increased. But with increase of viscosity, the flux will be reduced, and we have a membrane resistance. Resistance that is all of the resistance that cause to reduce the passing of a solute from a membrane. A membrane is mass transfer and moves from one location to another location. All of resistance that there is in this pass, road can name as the resistance of, for example, membrane pore size. With reducing of the membrane pore size, the passing is hard, is problematic, and with reducing of pore size, the resistance increases. Porosity. Porosity is the free space in the membrane body or in the membrane surface. With the increase of porosity, resistance reduces. High porosity, high flux. Affinity in some mechanisms, in solution diffusion, in ion exchange membranes, we have shown functional groups can interact, can attach, can affinity to a molecules or ions and give these molecules and pass and diffuse from the membrane body. This hydrophilicity, this interaction is important. High affinity, high hydrophilicity can cause the high flux. Surface charge, in some cases, the surface charge is very important in separation, non-filtration membrane, in fouling phenomena, the surface charge is very important. Membrane thickness, higher thickness, lower flux, and others. In lab, we usually have a membrane with specific surface area. We cut a circular membrane in 5 or 6 diameter and measure the flow. We use a vessel and collect the passed water and weight or measure the volume and in the specific time. With the measuring of the volume in time and we having the area, we can calculate the flux. Okay, very simple. Calculate the membrane resistance. We know that resistance of ultrafiltration membrane is higher than microfiltration because have low molecular pore size, low pore size. Usually for testing of the membranes in lab or industrial scale, we have 2 regimes of the flows. We have a dead-end filtration or we have cross-flow filtration. In cross-flow, we have a cross movement of the fluid related to the membrane surface. Here, the permeate side, but the feed is have a 90 degree with the permeate pass and the flow pass. Therefore, we have a cross. Okay? We say cross flow because the feed and permeate stream have a cross section. But in the dead end, the feed flow and the filtrate or permeate flow is parallel. In industrial case, we want mostly use the cross flow because the cross flow push all of the substance and foreign agent from the surface and sweep the membrane surface and reduce the concentration polarization and reduce the fouling. But in the dead-end method, we have a high concentration. We say this is the cake layer or gel layer. This cake layer and the gel layer increase membrane resistance because act as a barrier layer. as a barrier layer that increase the membrane thickness. First, the solute should pass from this thick layer and the next receive to the main membrane. But in the cross flow, the thickness of the concentration layer is low and the fouling is lower. Therefore, in cross flow, the fouling is lower than the dead end method. In industry, in most cases, we use the cross flow for reducing of the fouling, but in some gas separation, we have a dead end, or in a syringe filter that is used in medicals for separating of some things from the blood. We use the microfiltration membrane as a dead end method. As I said, that the membrane process is separation process, and we have a mass transfer in membrane also, but we have a difference, and that in this is video, but not there. In the membrane process, we have a vector for passing in this random mass transfer, but in the membrane, we have transfer from left to right, and we have a vector, and for producing this vector, we need driving force. That's delta P, delta E, delta C, cause to the passing in a line and in a vector form. We have a diffusion. We have a diffusion mechanism in membranes, and this diffusion mechanism can be increased with external force. With external force, we increase the diffusion coefficient in fixed laws. Fixed laws, we have DRB. In D, with external force as a pressure, we increase this constant for passing from the membrane. Generally, separation processes has in single phase or between two phase. As you know in mass balance lesson, you know that in single phase we separate from liquid to liquid. Or in the between two phase, we have two different phase: gas liquid, gas solid, liquid liquid, or liquid solid. Most of these processes is direct contact or direct contact. That means that the liquid phase direct contact with gas phase. But in the membrane, we have indirect contact. That means we have a barrier and no contact between the two phases. But we have a mass transfer between two phases. All of this process have a mass transfer, okay? One solute, one species, separate, for example, from liquid to liquid. Liquid extraction, we have a water phase and liquid phase. One samples adsorb to the organic phase, and this separate from water phase. But in membrane, we have a indirect contact, and this cause that we have a pure product relatively. We have a mathematical equations for discussion about the membrane flux and permeability. As a general equations, we have a delta X per L. L is the thickness of the membrane or the road that from A to B, the mass should be transferred. Okay? We have a 2 point A to B. In mass transfer, the distance is important. This distance is L. In the membrane science, this distance is membrane thickness. Therefore, if we fabricate the thinner membrane, the flux will be increased. Therefore, we must prepare 100 micrometer membranes because the flux is very important in membrane separation. And delta X is the driving agent. Delta P, delta E, delta C, delta T, that generally is named chemical potential difference. Delta X, chemical potential difference for passing of a particle, a molecule, from point A to point B need a chemical potential difference. And this chemical potential difference can be pressure, temperature, concentration, or electrical potential. Usually, we have a passive transport. Passive transport means that we go from high potential to low potential. All of molecules want to reduce their energy, their potential, and therefore in passive transport, we go from high temperature to low temperature, high pressure to low pressure, high concentration to, but this is a passive transport. But we have a non-passive transport. That means active transport. Active transport is the reverse of passive transport. In the passive, we go from high to low, but in the active, we can go from the low to the high. This transport in membrane is named carrier membrane or facilitated membrane, facilitated transport. In this facilitated transport or carrier mediated transport, usually used in liquid membranes, we have a special agent, such as a complex, that this complex ligand, complex molecule, can connect to the, for example, heavy metal, and extract the heavy metal from low concentration to high concentration. This is the fit site. This is the permeate site. In active transfer, we have a low concentration to high concentration, but for this transform, we usually need a carrier that you see, which show with C. This carrier come, interact with A, and go to the permeate site and release. For this attachment and release, we need a change in a response. For example, here we have a pH 8. Here in the permeate side, we have a pH 4. With change of the pH, this carrier can complex with metal, and with reducing the pH can release. Okay, this membrane is also named as intelligent membrane or responsive membrane with the change of temperature, with change of the pH, or with change of the concentration, with change of electricity, they can adsorb or dissolve. And intelligent or smart membranes. But this gradient also say this also is problem with this. Based on the driving force, we can different membranes for pressure gradients. We have a microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. In the microfiltration, you see we can separate big particles. We can separate bacteria, particles, and others, not good see. This here is better. Red bloods, but in UF we can reduce, we can separate. In UF we can separate virus, gelatin, and generally macromolecules. In nanofiltration, we can separate the synthetic dyes. Molecular weight is 1,000 gram per mole. Heavy metals can separate calcium 2 plus from sodium 1 plus, sulfate 2 minus from chlor 1 minus. But RO separate all of the solids. Okay? When we use the RO can separate all of these ions and molecules. One question is why we not used RO for separation of this, when we can use one process for separation of all these molecules. Why we use MF? Why we use UF? We can use RO for separating of all of them. But with going from right to left, microfiltration, UF, NF, and RO, we need to high pressure. And high pressure means high energy. Therefore, the energy consumption of RO is very, very high than MF. In MF, we use 1 bar pressure, but in reverse osmosis, we use 30 bar, and therefore need to high energy. Also, the flux of MF is very, very high than RO. Therefore, when we can separate solutes with lower pressure, lower energy, and high flux, we no need to use the RO. Therefore, RO is used for desalination and is the high price technology. Based on the concentration gradients, we have a dialysis, evaporation, gas separation, and liquid membrane processes. We have 22 membrane processes. I can present in this slide. For electric gradients, we have electrodialysis membranes or electromembranes that I will discuss after noon, these processes. And for temperature gradients, we have a membrane distillation. That in membrane distillation, the vapor passes from the membrane, not liquid. And with using of membrane distillation, we reduce the energy of distillation process and use for very, very high concentration. Usually MD used for concentrated solution of reverse osmosis. About morphology and structure of membranes, The membranes can be porous or non-porous. Membranes can be porous or non-porous. Membranes can be symmetric or asymmetric. Can be isotropic or anisotropic. Symmetric equal to isotropic, asymmetric equal to the anisotropic. Symmetric in the membrane is not right and left. Symmetric is top and bottom. Very small. You see in this, the right and the left is similar. But when the membrane is anisotropic, means that the top and the bottom is different. You see that here in the top layer, we have small pores, and in the bottom layer, we have big pores. Therefore, this is a asymmetric membrane. Or in this case, we have a non-porous layer coated in a porous support. Therefore, the top and bottom is different. In this type, that we have a thin layer on the support, the membrane is called thin film composite. Thin film composite, TFC membranes. In TFC membranes, we have a very thin layer, non-porous layer on the support and used in reverse osmosis, nanofiltration, gas separation. And these membranes usually have very high flux rather than this dense membrane. In this scanning electron microscopy, you see the real SEM image. So the right one is the symmetric, the top and bottom is similar, and is the porous, and have a spongy structure. We say that the structure of membrane is spongy. In the left, we have a finger-like structure, similar to the finger, and we have a finger-like and have a asymmetric. Asymmetric, that means the top layer pores is smaller than the bottom layer. When we zoom, that see that this pores is smaller than the bottom layer, and this membrane is also named as Loeb Sorirazan membranes. Huh? Okay, well.
So that they can reconnect the.
Okay, perfect, thanks. One hour is low. My slide is not comprehend. The one. I continue 30 minutes. Yes, finish. I send rapid speed. I will come. Huh?
So if you continue, then I will start my session after the.
No, you. Afternoon, you present your lecture, and if my presentation is not complete in the tutorial, I speak about this and continue the lecture. We have we can. Okay.
meet up, whatever you take need time to complete your session. So that will plan.
Okay.
Have a lot.
Okay.
It's going good. Thank you.
Okay. Is there a question? You can ask your question about I discussed up to now.
If the participants have any questions or would like to interact with the presentation, please feel free to talk. Because we have okay, now we are okay, fine.
Okay. As I discussed, the membranes can be porous or non-porous, and the porosity can be different, such as finger-like, spongy, macrovoids, mix-up spongy finger-like, and very different structure. But usual structure in the membrane is non-porous, spongy porous, and finger-like porous. But we have other structure also. Based on this structure, we can different separation mechanisms. In the porous membranes, we have usually size exclusion mechanism. In size exclusion, our molecular sieving mechanism, we have a porosity that the small molecules can pass, and the big molecules cannot pass or low pass. Therefore, in porous membrane, the main mechanism in one separation, maybe we have three mechanisms together. For example, size exclusion mechanism, adsorption mechanism, and charge retention mechanism. But generally, in porous membranes, we have a size exclusion mechanism that's called also molecular sieve or IL sieve mechanism. In non-porous membranes, we have no density, no porosity, we have a dense membrane. We have no porosity and we have a dense membrane. That means we have no pores. And in this case, we have solution diffusion mechanism. We have two steps. One, molecules should be first adsorbed on the membrane surface. For this adsorption, need affinity, need functional groups for interact the molecules from the membrane functional groups. And after adsorption, in the second step, the molecules should be diffused across the membranes. The flux of the solution diffusion is very low, and the flux of the porous membranes is high. In the second mechanism, as I say, that active transport, we have a carrier that this carrier only reacts with black species and after passing from release from the permeate size. Therefore, we have generally three important mechanisms in the membranes: that size exclusion, solution diffusion, affinity, and in some cases we have a adsorption mechanism. Similar. Okay. In this slide, we show that the also adsorption mechanism. The polymeric membranes can have the adsorption properties and can separate some molecules, some ions with adsorption capacity. But adsorption capacity can be freed after the certain time, and this membrane is usually used for low concentration of the feed or for low times. And usually adsorption membranes is used for one times and used in, for example, silic filters for separation of one special molecules from the liquid. We can also have electrostatic repulsion that used in the nanofiltration membranes. When we have, for example, a negative charge on the membrane surface, this negative charge can reject the negative solutes. We have a positive and negative solutes. Positive solutes adsorbed by the negative charge and pass from the membrane, but the negative ions or molecules reject. This mechanism is called Donan mechanism. In Donan mechanism, we see that the anions most rejected than cations. There are different equations for discussion about the mass transfer in the membranes. For example, Hagen-Poisson, that you see this equation is similar to the mass transfer equation. In the mass transfer equation, we write that G is delta X per R. We see that for passing of one species from the membrane, we need the driving force, and we have a resistance that's against the passing and have resistance to pass. In these equations, for example, Hagen-Poisson, the R is defined and divided to the influencing parameters. Delta X is delta P, and R is equal to this ones. Delta X is the thickness of membrane. Higher thickness, lower flux. Viscosity, higher viscosity, lower flux. The pore size with score that shows that the pore size is very important than others. With increasing of pore size, flux increases, and epsilon is the porosity, surface porosity. With increasing of porosity, the flux increases. We have a constant here that's called as tortuosity. In this Hagen-Poisson assume that all of membrane is cylindrical. But in actual, membrane's structure is different. This is cylindrical. If the membranes have cylindrical pores, the top or tortuosity will be 1. If we have finger-like structure, the tortuosity is 1.5. And if we have a spongy structure or ceramic membranes, we usually use this amount in equation. The second problem is the use of overall porosity or surface porosity in Hagen-Poiseuille equation. In Hagen-Poiseuille, we must use surface porosity. Overall porosity is influenced in the flux, but the important parameter is surface porosity. In this schematic, you see 3 membranes, different membranes, that these membranes have small pores, medium pores, and big pores. Okay? But 3 membranes have equal porosity. I want to say that surface porosity is different from pore size. Maybe pore size is big, but porosity is small. We cannot correlate the pore size to the porosity. Many researchers say that with increase of pore size, porosity increases. It is not true. You see in this schematic, both have equal porosity. Porosity, that means the area of pores to all areas of the membrane. And in the 3 images, we have an equal porosity, but the pore is different. Another aspect is pore size distribution. Pore size different from pore size distribution. Pore size distribution, it means that how the pore size is similar together. When we have a similar pore size, it is very good from selectivity. And these membranes have a sharp separation. If we can fabricate this membrane, is very good, very interesting. If we have fabricated this membrane, we can publish in journals with impact 30, because very important, we have a unique pore size that is isoporous. But if we can prepare a narrow membrane, also is good. But usually, we prepare this membrane. That we have a very big pores and very low pores. Therefore, when we have a different pore size, the rejection will be reduced, and the selectivity will be reduced, and the fouling increases. When we have a bigger pore size, in the neighbor of the small pore size, this pore size can be filled with the foulant and block the pores. When the pores is blocked, we cannot recover the pores in the cleaning or washing, and the membrane will be destroyed very rapid time. Therefore, in the view of the fouling, for reducing of the membrane fouling, it is better we have narrow or isoporous membrane. The right is better one, acceptable, but this bad membranes. Okay? This is another equation used in ceramic membranes mostly. And as you see, similar to Hagen-Poiseuille, we have a delta P thickness, porosity, and others. I pass. we have a MF, UF, NF, RO. We say this membrane is filtration membrane. Filtration membrane that you see the pore size of the MF is bigger than UF, UF is bigger than NF, and in RO we say we have not pores, or if we have, it is very, very small in angstrom scale, and we cannot see. Okay? Therefore, RO, not pores, or have very, very small pores. With reducing of the pores, we need a high pressure for transferring of the solids from the membrane. MF membranes separate bacteria, parasite, particles, but cannot separate the viruses. High molecular substance, these molecules separate from the UF, and the NF can separate the multi-charged ions. Mid-sized organic substance such as dyes, and RO completely separate, but most used for separation of ions, heavy metals, and salts. In application of the membrane, we have two types of pressure: direct pressure and vacuum pressure. Most of membranes use the vacuum pressure, and for applying of pressure, we use pressure vessels. This is not membranes. This is the pressure vessels that membrane modules located inside of this pressure vessel, and this pressure vessel is used for applying pressure. And we can apply higher pressure. But in vacuum pressure that we submerge, immerse the membranes in the water, we apply vacuum pressure with suction pumps, and mostly, and the highest pressure that we can apply in vacuum is 1 atmosphere. We can only produce 1 atmosphere vacuum, and therefore this method, vacuum, is used MF, UF, and pervaporation membranes for separation, because in this process we need lower pressure. Other methods usually used and is the famous in the membrane is reverse osmosis. As you know, we have a direct osmosis. In direct osmosis, the pure water adsorbs to the saline water or sugar water. But in reverse osmosis, we want to separate water from saline water, not pure water go to the saline water. Therefore, we must apply pressure. This pressure should be overcome to the osmotic pressure. When we have a high concentration of the salts, the osmotic pressure increases. The osmotic pressure of the seawater is higher than the well water, groundwater. High salt, high osmotic pressure. Therefore, we must apply pressure first for overcome to osmotic pressure, and second for passing of the membranes from reverse osmosis. The mechanism of the separation in reverse osmosis is solution diffusion, and I discussed that in solution diffusion, the solvent, mostly water, adsorb on polyimide polymer. Polyamide polymer is hydrophilic polymer, and pass and diffuse from the polyimide and goes to the permeate side. The diffusion process, solution diffusion process is very slow process, and therefore we must prepare a thin layer. We have a top layer, you see, this is the structure of the RO membranes. We have a non-woven baking or non-woven fabric for increasing of the membrane durability, membrane strength. We have a polysulfone support layer for supporting this polyimide thin film layer. You see the thickness of the active layer and selective layer is very low, nanometric layer. If we prepare this layer, instead of this amount, we increase, for example, 1,500 nanometers, 10 times increase the thickness, we will have no any permeate because the diffusion is very, very low, and therefore we must prepare a very thin layer. But thin layer has not good stability, can be easily tear, and therefore we prepare this layer on a support for increasing of the stability and durability. The main layer, this active layer, selective layer, and these two layers is supporting and increasing the membrane stability. You see, for fabrication of the RO membrane, we use interfacial polymerization method, and polymerization, you see that we have a very angstrom scale pores. And in these pores, the water only can pass, and the hydrated salts, such as sodium and chloride, cannot pass. Because one sodium hydrated with 6 water and have a big size and cannot pass. Another separation mechanism, as I discussed before, Donan exclusion. In a Donan exclusion, the charge of the membrane is important. When we have a negative charge, on the membrane surface, you see that the sulfate ions with 2- charge more rejected. After that, sodium chloride, and after that, calcium chloride. We have a negative charge on the membrane surface. The sulfate has 2- charge. 2- charge. Therefore, the membrane with the negative charge more reject the sulfate. Okay? When we compare these two, NaCl with Na2SO4, the sodium is similar, but sulfate have more rejection from color, because color have 1-. Okay? Therefore, the phosphate with a 3- will be more rejected from sulfate. But when we compare the chloride, color is similar, but sodium and calcium. Calcium have 2+. Okay? you see that the color is similar, but change of the sodium to calcium, the rejection is reduced. Why? Because this calcium can adsorb on the membrane surface and neutralize the negative charge. Positive charge can neutralize the negative charge, therefore reduce the negative charge of membrane, and the selectivity is reduced. In the positively charged membrane, the trend is reverse. In positively charged membrane, the calcium 2 plus more rejected, sodium is moderate, and sulfate is lower. Therefore, in lab, if you have nanofiltration membrane, with test of these results, you can find that this membrane have negative charge or positive charge very easily. But for measurement of the membrane sulfate charge, we usually zeta potential device that, but this simple example can go that our membrane is positive or negative. Nanofiltration membrane have two types. One type mostly reject with Doman exclusion and have these trends, but some nanofiltrations membranes have a low charge or no charge, and this low charge no influence in the rejection. And in this case, the rejection you see in the previous slide, calcium is bottom of this NaCl. In this case, the diffusion rate is important, and if the molecule hydrated size of the molecule is low, the rejection will be low. We have metal. I speak about the mechanism of separation. In the metallic membranes that used for hydrogen separation, if we have a very thin metal layer prepared from palladium, nickel, cobalt, this only hydrogen membrane. In metallic membranes, non-porous metallic membranes, only hydrogen can pass because hydrogen is very small and highest diffusion coefficient. In this mechanism, hydrogen can go to the membrane surface and dissociate it to the hydrogen atoms. Hydrogen atoms pass the membranes, and the permeate size, again, hydrogen atoms connect together and produce hydrogen molecules. This take only in the surface of these metals, and this membrane is expensive, but mostly used in petrochemical processes, for example, in Haber process, for fabrication of ammonia. The methane in petrochemical process, methane changes to the carbon monoxide and hydrogen should be separated from monoxide to production of ammonia. These membranes mostly used in this industry and have very extraordinary selective, because only hydrogen gas can pass from these membranes. And as the final slides, we have ion exchange membranes. In the ion exchange membranes, we want to pass cation from cation exchange membrane, and anion not pass. And for example, in this slide, for passing of the positive ions, we need two negative functional groups on the membrane structure. We have many polymeric chains. We have many polymeric chains with the functional groups of this negative charge can be sulfonic acid, can be carboxylic acid. This carboxylic and sulfonic acid can be adsorbed proton, can be calcium, can be magnesium, and we have a hopping mechanism. In ionic sense, we have a hopping mechanism that we have many membrane chains together, complicated, and have the noise and the moving. And in this moving, one functional group can contact to another. This contact to another and transfer one cation from this functional group to another. And we have a hopping mechanism to separate. For this driving force, for this movement from left to right, we need a driving force. And this driving force is electrical charge. In these membranes, we have electrodes. If we want to cation pass from the membrane, we must have a negative induction of electrical field to adsorb, to force the positive charge go to the negative electron. Driving force is electrical charge, and the mechanism is the hopping between the functional groups of this. This hop to this hop to this, to this, to this, and go to the electrode side. Thank you for your attention. I try to introduce the general science of the membranes in this lecture. And in other lectures, we focus mostly and we speak mostly, for example, in ionic sense mechanism and application and other information.
Thank you, Professor, for the lecture. So I now request the audience to ask any questions what you have. So if the audience have any question, please feel free to discuss.
Thank you. It was such a wonderful and very informative talk. And I think most of the beginners also must have had a very good introduction on the topic. I just had a query, like the surface potential based or the donor exclusion part that you have explained, that is valid for both ultrafiltration as well as nanofiltration, right? Or it is only for the ultrafiltration membranes?
About the donor exclusion, we can manage the charge of the membranes with selecting of the polymers and functionality. Most of the polymers have negative charge, and this charge also related to the pH. With change of the pH, the charge is changed. Usually the wastewater pH between the 6 and 8, and when we say that negative charge or positive charge, we tell in this range. For positively charged, we usually use amine groups. With addition of amine groups, we can use positive charge. And with negative charge, with hydroxyl, carboxylic, our natural carbonyl groups, OH groups can have a very low negative charge. This charge, in most cases, can influence the rejection, but I say that we have not only this mechanism. In the separation, we have a mix of the separation. For example, we have a more big pore size and we have a more negative charge. We cannot separate these salts. First, the pore size should be reduced to 3 nanometers, 4 nanometers, and next the pore size will be, the charge will be influenced in the separation.
Like we are currently separating lithium, so we are using ultra 4 only.
Yes.
Shift to sulfate.
Yes.
So this
Now, separation of lithium from magnesium is very important for production of batteries. And the lithium rejection is lower than the sodium because lithium is smaller. For increase of lithium, we must use the non-porous membranes, usually, TFC membranes. And the nanofiltration rejection is not suitable for lithium. In recent studies, usually use positively charged membranes for separation of lithium because the counter-ions in lithium is mostly carbonate. And carbonate is better rejection with positive membrane. Therefore, if we want to use the nanofiltration for separation of lithium, it is better we increase positive charge for increase of the salt of the counter-ions, not lithium.
Thank you. Thank you so much.
So let us maybe please join me in thanking Professor for his academic presentation. And so I ask the participants whether they want to continue with the second lecture or should we go for lunch first and then continue the second lecture. Most of the participants were opted for second option. So with that view in mind, let us proceed for the lunch and then we will gather at this point at sharply at 2 p.m. The second lecture, so is it okay if I continue with the second lecture or should we want to continue with the evening?
No important for me, as you say.
Okay. So then I will continue. I will start at 2 p.m. and then we will second professor will continue. So let us proceed to the last at 312. Okay. At 2 p.m. we shall join. Thank you.
Thank you. Thank you. After lunch.
Good afternoon, everyone. Myself, Raka Mondal. I would like to start the second session with me today. So, this session or this lecture is about the hydrogen energy and the membrane that is used for hydrogen generation. So, in this session, we are going to learn about the types of membrane that we can use for this technology. We are going to talk about the different applications of specific membranes in specific hydrogen production technologies. How do we choose the properties and how do we analyze these membranes? The state-of-art membrane technologies, cost and efficiency analysis, and some industrial case studies. Hydrogen. It is not only a crucial form of energy, crucial form of fuel for production of energy, but also it is used in different parts of industry for different production purpose. It is used in fuel cell as a fuel to generate energy. It is also used in petroleum refining, ammonia production, and importantly, the most important contribution for hydrogen is that it is a clean fuel source. The hydrogen production methods include steam methane reforming, which is the most common used industrial method till now, it uses natural gas to produce hydrogen. We can also have electrolysis where the electrical energy is used to degrade or to degenerate the water molecule, and in that way we can produce hydrogen and oxygen. We can also have biomass gasification where the organic materials are converted to generate hydrogen. Photocatalysis, which is having a very good research focus nowadays, it uses sunlight directly to have the lysis of oxygen water molecule to generate hydrogen and oxygen. Membranes play a very crucial role in all of these production methods. They not only enhances the efficiency, it reduces the overall cost, it improves the purity level of the hydrogen, which is a very important. It controls the emission of greenhouse gases, and it can contribute to a sustainable future. Now, with the method of hydrogen generated, the hydrogens are divided into three main categories. First is the grey hydrogen, which has been most widely used till now, which I was telling that it uses natural gas mostly, basically fossil fuel is used. So as a result, what we see is that we see a lot of CO2 generation. So it is carbon positive, that means we are generating or we are emitting carbon towards the environment. So it is not very environmental friendly or sustainable process. But what we have now is that our focus is slowly shifting towards blue hydrogen, where the carbon dioxide is stored underground. So these are either underground or any other CCUS method or carbon capture and storage method. So what we are doing here is that we are not emitting the carbon dioxide directly to the environment. So that is why either it is carbon neutral or it is not carbon positive, or carbon footprint is much lesser for blue hydrogen generation. Whether in green hydrogen production, we do not have any CO2 generated. So it is a most convenient or most sustainable process we can have. But in order to have a large scale production of green hydrogen or to shift our entire hydrogen production towards the green hydrogen production, we need a lot of research focus. Now, let us say what are the typical membrane based hydrogen production technologies. In membrane reactor, we can produce hydrogen where the membrane in the reactor, it acts as a medium for reaction, it provides the surface area, it also acts as a selective, it enhances the selective transport through the membrane. So in our first lecture, we learned a lot about the transport mechanism through these membranes. So most of these principles of transport through these membranes are applicable in this type of membrane also. We also have PEM or the proton exchange membrane, which is mostly used in the electrolyzers and the fuel cells of PEM category. So what does it do? It carries the hydrogen from the anode side to the cathode side, but also does not let the hydrogen and oxygen mix. We have to keep in mind, if the hydrogen and oxygen mixes, there is a very high chance of fire or accident. Okay. So the flammable limit is 4%. So we cannot have more than 4% mixing of hydrogen and oxygen. So we have to have a membrane which is very efficient in separating them. Okay. Now we also have steam methane reforming, where the hydrogen the membrane is used for enhancing the purity of the hydrogen. We also have WGS or water gas shift reaction, where the carbon capture happens through the membrane. Okay. Now basically the role of the membrane in all these categories is transport, selective transport. So which to pass and which not to pass through these membranes, that is the most important thing. Okay. So that is how we can have a good efficiency of our process. Operating conditions also vary quite a lot based on the type of method that we are using, based on the conditions that we are using. So that way you can operate a membrane at a room temperature, like in PM you can operate up to 80 degrees centigrade with the conventional membranes, but in MCFC or SOFC, some special type of fuel cells, you can go up to 800, 1000 degrees centigrade. So it depends on the type of operation that we are using. Similarly, the composition of the membrane, that will also vary based on the production method. It is used in form of integrated into these fuel cells, like as it is being shown here. There are some high temperature fuel cells like MCFC and SOFC, where the metallic membranes are captured or sandwiched between the anode and cathode side, and we have selective transport of some ions. Okay, they operate at very high temperature. They are integrated here, this PEM or electrolyzer. Here we have integrated this membrane, PEM membrane between the anode and cathode, where it is efficiently blocking the intermixing of hydrogen and oxygen and also selectively transporting them. Now, one challenge which is still remaining, which we need to address more to have a widespread applicability of these technologies, is that the membranes tend to degrade over a long time. So they have a limited lifetime. After that, these transport properties or this efficiency that goes down. So we have to be careful about what is the lifetime of the membrane, and we have to have a more high lifetime, so that the process can be more economic. Okay. So the research is going on to develop advanced material, to develop more cost-effective material. Now, what are the different types of membranes that we use? The types of membrane, as I was telling about PEM membrane, that it is in PEM electrolyzers. We can also have different other types of polymeric membranes also. So, as Professor Vedanpur was mentioning in the first lecture, that there are lots of options for polymers. That we can make membranes with. There are lots of variations with the polymers. But they are not only cost effective, they are moderately selective, but one disadvantage or one challenge, I should say, in the hydrogen production particularly, is that their selectivity is comparatively lower than the inorganic membrane. Whether we want the membrane to be more porous in liquid filtration, but in gas filtration or this kind of application, we need it to be dense so that the intermixing does not happen. We can have inorganic membrane, and palladium based membranes is a part of inorganic membrane which has been most popular. What is palladium based membrane? Palladium based membrane is nothing but some membrane which is mostly made up of palladium. Either some other materials is mixed with it, or it is solely made of palladium. What does it do? It converts the H2 form into the H plus form, and then it converts it or transports it through its one side to another side. That is the role of palladium. Now, it gives you very good efficiency. It gives you almost 100% separation of hydrogen and other gases. One challenge here with this palladium, it is that it is very costly. So, if it is costly, then a large scale production of palladium, it is limited. We have other options in inorganic membrane which are made up of ceramic, silica, zeolite, etc. We can keep in mind that inorganic membranes are very highly stable thermally, and mixed matrix membrane, whether they are stable but they are not very highly cost effective, but mixed matrix membrane, it actually, what does it do, or mixed matrix membrane or the composite membranes, it joins the goodness of these two. It joins the goodness of polymeric membrane and the inorganic membrane. So, it can be more scalable. So, where we are infusing some inorganic material into the organic matrix for mixed matrix membrane, it is making the membrane more porous but more selective at the same time, and also it is making it more cost effective, so that we can go for more scalable approach, more application in the real life. So that's why many researchers are mostly focusing on this mixed matrix membrane, or what we call it as a composite membrane in general. So if we look into the polymeric membranes, one of the type of polymeric membrane that is very popular is glass polymeric membrane. It is mainly thin film composite membranes are of this category. So they are not in particularly thermodynamic equilibrium, so they are very rigid in structure. So they offer very high selectivity compared to the other conventional polymeric molecules. They are very thin, they offer very high rigidity, very high selectivity. They are very dense in nature. And also there are other types of polymers like rubbery polymers. So we have learned a little about the polymers like PSF, like speak, these kind of polymers. They are rubbery polymers. They have comparatively higher permeability. They are more flexible, they are more economical. But they will have their particular advantage and particular challenge also. Mixed matrix membrane can be a mix-up of organic and the inorganic molecules. Where they are particularly advantageous? They are particularly advantageous in PSA type application. It is pressure swing adsorption. So in the membrane separation unit, the energy demand can be comparatively lower. It is again applied together with fuel cell, refineries. It can be effective in separation of the hydrogen with the syngas and biogas for different hydrogen generation method. It is low cost and lightweight. It is highly scalable. It is also energy efficient because it is more permeable than the more denser membranes. The limitation or the challenge is that we need to improve the selectivity. We need to improve the sensitivity towards temperature. It should be more stable at higher temperature also. So research is going on into that direction only. Now, what is PM membrane? PM membrane, as I was telling that PM membrane this is a typical structure of water electrolysis. So what we are seeing here is that we have given the water molecules towards the anode side, and with this catalyst anode, what it is producing, it is producing some protons, and in these protons is transported towards the cathode side, and there it is reacting, or this is getting the electron from the cathode side and generating hydrogen like this. In the anode side, the oxygen remains and the unreacted water remains, and it goes out. So this oxygen and this hydrogen can be effectively separated by the membrane. At the same time, they should effectively transport the hydrogen molecules, protons, so that they should not be the rate limiting step in this whole case. The main advantage of this is that they provide a very compact design. So that's why we will find a lot of application for PM technologies in transport sector, in car, in our space station. So there are a lot of application for PM membranes. They have offered very high efficiency, 75%, 85%, but they do not have a very high energy output. So we cannot give it or use it for a grid electric generation. Okay. The main type of membrane that we use is PTFE. The commercial name is Mafion, and it gives you proton conductivity around 120 millisiemens per centimeter at 80 degrees centigrade. But what it does is that above 80 degrees centigrade, its conductivity goes down. So we can use some catalyst to improve the efficiency, but at the same time losing the cost effectiveness. It can give you very high purity oxygen. Okay. So when we combine this PM technology or this electrical current source with a renewable power source, it really becomes very, very green technology in nature. Now, the inorganic type of membranes, they are made of palladium alloy, or other metal membranes like nickel, vanadium, etc. They are very highly stable, high temperature operation can be done with this inorganic membrane. So here mainly hydrogen gas dissociates, proton diffuses, and this gives you a very high purity. So you can use it for SMR, steam methane reforming, water electrolysis, ammonia cracking, etc. It is very common in fuel cells, especially the high temperature fuel cell like MCFC and also SOFC, etc. We can have the advantages of this is that it gives you very highly selective, very high purity. It is more durable than your polymeric membranes. It is compact, it can be made compact, which is not as small in size in PEM, but it is highly engineering or tailoring of its structure can be done with this. But it has a drawback of, or not drawback, the challenge of a high cost, and it can be fragile at some selected situations where there is poisoning by carbon monoxide or sulfur like this. Now, why palladium? I was telling that palladium has been most popular among the all different types of hydrogen membrane. Why? Because it gives you, it can operate at a normal temperature of 300 to 600 degrees centigrade. So remember that if you need very high temperature for your membrane to operate, then you are losing the energy efficiency. You need high amount of energy to increase the temperature. So if it can operate in that particular range 300 to 600 compared to other inorganic materials which requires even higher temperature, then it is a plus point for palladium. Now its permeability is also very good, but one challenge is that it is very sensitive to sulfur, and also it is very expensive. Possible enhancement can be by introducing some other materials, by making alloy like silver, copper, etc. alloy can be made, so that the cost effectiveness goes higher, and also we do not lose the permeability. And next I will come to next type of membrane, that is a ceramic membrane. So what is ceramic material? Ceramic material are even made up of some particular components which are highly temperature stable. So what does it do is that they work at very high temperature, like more than 500 degrees centigrade. It does not, so it gets activated at more than 500 degrees centigrade. It selectively transport the hydrogen. It can be engineered very effectively, like here I am showing, here they are showing some ceramic materials in a magnified situation, where you can see that the pore structures are very uniform. This is one advantage of inorganic or ceramic membranes. The pore structures it can be made very uniform, which is normally usually very difficult in polymeric membrane. So now the advantage is that it gives you very high temperature sensitivity, it is resistant to chemicals, it is highly durable, and it stays on for a very long time. Now composite membrane can be made up of polymer and metal, ceramic and polymer, or can be mix up of all these three, or can be any types of, they are generally, we call them different types of composite membrane, where the mixed matrix membrane is a subset of a composite membrane. The working principle, what is the advantage of this kind of composite membranes? That I was telling that it is adding up the goodness of the polymer and the inorganic also. So what we can have its application in different, we can have it as a different layers. So we can have a layer of polymer, on top of it a layer of inorganic, or other way around, inorganic and then polymer, or we can have, which is the layer by layer assembly, we call this a layer by layer assembly, or we can have it infused, the inorganic material can be distributed towards the membrane. Even there is a possibility that you can make throughout the, so let us say that this is my membrane thickness. So I can selectively concentrate some inorganic material towards the one side. So let us say that I am concentrating some palladium nanoparticles towards one side of my membrane, polymeric membrane, so that they will offer the sensitivity towards the anode transport, towards the hydrogen transport, towards the transport through the membrane. So based on the gradient of mass transfer, based on the gradient of potential, you can decide which way to concentrate your inorganic material more. So that's why they are called very highly tailor-made. They can be very highly tailor-made. They can be very useful in some specific application. So advantage is that they are cost effective, because they are not using too much of inorganic material, they are cost effective, they are having very high thermal and chemical stability, they are highly selective compared to normal mixed matrix for very high open pore membranes, they are more selective. But one problem is that their manufacturing process needs to be simplified to have it very high large scale application. One problem, another problem that we have been learning about, that Professor Vatanpur works extensively on this, fouling of the membrane. So if we have fouling of the membrane, this transport property goes down. Now let us look into a little bit of the more conventional membrane, more conventional hydrogen production process, which is called the SMR, or steam methane reforming. In the steam methane reforming, what do we know? That our carbon monoxide and water, that is converted to hydrogen and carbon dioxide. That is basically the method of, that is basically the reactant and the product of SMR. Now, in this process, we need some catalyst, and if we can immobilize those catalysts onto a membrane, then what it is giving you is that it is giving you the immovable catalyst particles or more areas for mass transfer. So that is how you can enhance the total mass transport rate, you can enhance the reaction efficiency. So if the membranes are made up of, if the reactors features these membranes, they can also they can be also made to capture the carbon dioxide. How? So if you say, let us say that I am using in a SMR, I am using a carbon dioxide capturing CCU capturing MOF or many other adsorbent for carbon dioxide capture, so that it can act as a CO2 capturing mechanism also. So not only in transport, but it will also attract the CO2 so that you can shift towards the green carbonate from the grey side of the hydrogen. Now it works, these membranes, this reaction, they works at a very high temperature. So we need that kind of membrane. So that is why mostly ceramic and palladium membrane based membranes are used in this type of operation. We generally prefer not to have purely polymeric membrane. The membrane advantage, I told you already, the advantages are high purity, energy efficiency, lower carbon emission, but the challenge remains about the durability of the membrane, because this is a high temperature operation. Again, with a prolonged use, its transport property goes down. So that is why we need to have a cost reduction also. We need to focus more on a hybrid system. Okay, so I have talked about the SMR, which I told that it is mostly grey, but grey produces grey hydrogen. So, but if we can engineer it in effective process, so that we can make it more carbon neutral, so carbon footprint can be reduced. But what is thought of a more greener technology is electrolysis. So practically passing electric current through the water so that they can be dissociated. Now, whether this process is challenging, but one method that is very well used is that you have a liquid cell where these two anode and cathode side, they are separated like a diaphragm. Diaphragm is nothing but a special kind of membrane. Now, what happens is that these diaphragm, when we are providing more of a liquid environment, then they are seen to be because the pH is highly varying from one side to another side, because the electric current, they are seen to be degrade very rapidly. So that's why many people, they are focusing mostly on PEM or AEM electrolysis, where the membrane itself acts as an electrolyte. So their role is to transport these oxygen and these ions, and they are separating also the oxygen and carbon. So we are avoiding this extreme variation in the pH and the ionic variation, so that our setup can be more stable. Whether if we have a very high power output requirement, we can go for technologies like SOFC or MCFC, etc., where inorganic material or ceramic material, it can be a more preferable choice. Now, the working principle is that the membrane, they do not split the water molecules, they are just using the transport mechanism through them and the selective transport mechanism through them. Now, the challenge here still remains if we can use it for long term stability or for a higher temperature operation. Next, let us look into a little bit about very green technology where no kind of there is very less probability of using CO2 generation. What we can do is that we can use a renewable source of energy like solar or wind to have the electricity generated and pass it through this electrolyzer setup, so that we can have this membrane, this hydrogen and oxygen generated. So practically in this setup, if we are applying external current and we get that external current from renewable energy, then like for photocatalysis energy like solar or this visible light, so then we make the membrane photocatalytic membrane, or make the process photocatalytic process. So the role of this membrane is to, they separate the hydrogen and oxygen, they go for ion conduction, they provide chemical stability, they provide more mechanical efficiency and energy efficiency also. The type of membrane that we use for this type of membrane is, the most common one is the Nafion membrane, or also we also use SPEAK. SPEAK is the sulfonated ether ketone, sulfonylated ether ketone. So what does it do is that it is more available than Nafion, but it also has sulfone groups. So what does it do is that, I'll just show you. So if this is the membrane, which is like on this side you have anode and you have cathode on this side. So it will have very small water channels through them. Very small water channels through them. So water channels is basically made up of polymeric backbone, two polymers of polymeric backbone, and they have, the polymeric backbones are hydrophobic in nature. They have some side chains which are giving you hydrophilic nature, so that this region between the two polymeric backbones, they are hydrophilic zones, but they have a boundary which is hydrophobic. So that's why it is making some water channels, or it is transforming, or it is enhancing the vehicular transport through which the water molecules are carrying one of the H plus ions through them. So like this, we make different kinds of water channels, and in SPEAK we make these more hydrophilic zones, hydrophilic side chains more, and this material gives a very good structure of these water channels. Now this is also found in different types of membrane materials like Nafion or anion exchange membranes or PERL membranes, etc. So this is a general structure of the membrane. They have varying thickness, and because of this thickness they are also resistance, not only because of this thickness but the internal structure. Therefore these also, their conductivity, their stability, that varies quite a lot. Characterization techniques are SEM, which tells you about the morphology, whether there is any uniformity or non-uniformity, or whether there is defect. So all those kinds of things can be analyzed through the SEM, high magnification images. It gives you a crystalline nature structure if you analyze it through a XRD. So if your membrane is crystallinity is good, then the resistance towards the ion transport is less. So that's why we need a good crystalline structure or stable crystalline structure in the membrane. FTIR, it gives you the exactly what kinds of side chains are there in your membrane, so that you can have a good idea that whether it is which type of ions it can conduct very efficiently. You can have AFM. AFM is a surface morphology. it is giving you. So whether you need to have very low roughness onto your surface also, because if the rough surface is very rough, then the contact between anode and the membrane or the electrolyte, it is very poor. So it gives you additional resistance to your transport system. Okay. You can have gas permeability testing, as I was telling that gas permeability should be less. It should be selectivity, it should be highly selective of hydrogen over the other gases. It should be mechanically strong so that it this in the high pressure environment it can be stable. Thermal stability, it should be for ceramic membrane, should be very highly thermally stable. For durability, we have chemical resistance. So we expose these membranes to different substances like H2S, CO, etc. steam for very long hours, like 1000+ hours, and we see that what is the mass loss or what is the structure changes in the membrane. We also do cyclic changes. So we evaluate the membrane performance under varying pressure, varying voltage. So with these conditions, how the membrane is, how many cycles it can sustain. We do also aging tests. So with very long time, how long it is staying good. So with these are the mainly typical characterizations that we do for different kinds of such membranes. There are different standardization or certification that is available, whether this membrane is good for practical use. For that we have ISO standard, we have ASTM standard. Basically they are for gas permeability testing through the membrane. We also have DOE standard. For DOE has a fuel cell and hydrogen program which establishes the durability structure and efficiency benchmark of the membrane. Okay. As I was telling you about different membranes, they have different types of properties. So if you compare, the polymeric membrane gives you very high permeability, but the selectivity is comparatively lower. And this is basically a summary of what I have told you about different types of membranes. Operating temperature for the polymeric and inorganic is in that range, but the stability is very high for ceramic membrane, high for inorganic and metallic membrane, but moderate for polymeric membrane. Mechanical strength is low for polymeric membrane because it gives you more porous structure, but its chemical stability is moderate also. Thermal stability, it has got specific applications in some specific categories, but inorganic membranes, they are of it is stable, it should be highly stable in very harsh gases because they are being exposed to very high temperature, very high operation efficiency. But metallic membranes has a drawback of they are very highly sensitive to sulfur content, which is not a very good sign for a mixed gas analysis or mixed gas separation method. Now, if we have a cost comparison, I should not say cost analysis, in the comparison of cost, polymeric membranes are much cost effective. So they are giving you option for large scale application. Inorganic membranes like palladiums, they are expensive comparatively. Ceramic membrane, they are comparatively less expensive than palladium. Metallic membranes are also too much expensive, but mixed matrix membrane can be a bridge between them and they can reduce the cost while retaining the efficiency. So the challenges till now is thermal stability issue, high cost, selectivity, membrane for this, and optimization it has to be done with these membranes. Okay. So we have some hybrid systems with the membranes, like we can have thermochemical or electrochemical process or biological process. So what are those? Basically biological process is where we have a membrane bioreactor, or I will give you some example that when we have a microbes immobilized onto the membrane process, not specifically for hydrogen production, but it is a very useful application for water purification technology. So we can have such kind of idea to be evaluated to hydrogen, but we have to find such microbes which are stable in that kind of environment. We can have PM electrolysis with 80 to 90% efficiency. So these are the solid oxide membranes and they have their typical applications for this. Okay. Next, I would like to talk a little about the nanomaterials, because nanomaterials, as we know that it enhances membrane permeability and selectivity by providing high amount of surface area, by giving you the good stability. But what it does, it reduces the material usage. So the total amount of palladium that you have to use, the total amount of inorganic material that you have to use, that is reduced. So that is why your cost is reduced. But at the same time, making of this material in a stable and highly effective format, that requires a complex processing. So what kind of nanomaterials are being used? These kind of membranes are basically nanomaterials being imparted into your composite membranes. So that kind of membranes I am now talking about. So where you have either a polymeric materials imparted in it, some nanomaterials in it. So what kind of nanomaterials you use? We can use graphene oxide. It enhances the hydrogen selectivity. We can use carbon nanotube. You can use MOPS. MOPS is a very popular choice nowadays for increasing the gas separation efficiency. It enhances the lifespan, which is a significant improvement over polymeric membrane. It enables operation at lower temperature, significant improvement over inorganic membrane, and reduces energy consumption, significant improvement over inorganic membranes. But a challenge or more research should be there on large scale production, as I was telling that the production process itself is a little complex. So that's why for industrial separation or industrial scale production of these membranes, we need a optimized technology for large scale process. So mostly when we talk about the composite membranes, this is the main focus of our membranes, that we should go on more towards the nanomaterial side, but should be also at the same time more stable. But let us see a little bit of industrial applications. So industrial application for hydrogen demand actually has already crossed by 2023 90 million tons per annually. So you can imagine the level of hydrogen demand that is there in all over the industries. PM has been deployed in 5 megawatt electrolysis plant with Nafion based membrane. Ceramic membranes, it increases, it has been in use in a lower scale separation, and future trends is that to have a scaling up of these membrane reactors for having a more green hydrogen production. The standards that we have for these type of membranes is that we should have a ISO 14687 for purity standard. For industrial use, ASME B31.12 for pipeline, and for semiconductor industries, very ultra pure hydrogen is required for this portion. But membrane efficiency, it needs a higher selectivity, so for that palladium is there, and operating conditions is that polymeric membranes for this industrial application, they operate at the 25 to 80 degrees centigrade. So what are the environmental factors that we should keep in mind? So palladium membranes, we should avoid sulfur. For pressure variation, we should, high pressure operation enhances hydrogen flux, but we need to keep in mind that prolonged use in very high temperature, very high pressure operation will make our membrane brittle. If we have any kind of membrane, this is true for any kind of membrane. But chemical exposure, especially for typical mixed matrix membrane, if we have exposure to CO2 and H2S, it reduces its lifespan. But longevity for industrial scale, if we reduce by per year, we get the efficiency reduced by 5 or 10%, then it is not very good for industrial standard. So for sustainability purpose, we have to have layer by layer assembly or advanced coating and composite membrane reduction in order to have a more environmental friendly application. temperature and humidity is a little bit sensitive because as I was mentioning about Nafion membrane that they cannot operate more than operate very efficiently at more than 80 degrees centigrade. Why? Because these water channels that I was telling you, they have very narrow constrictions. They require water molecules to carry the hydrogen ions. So hydrogen H plus ions. Now in this case, if we do not have sufficient level of hydration, what will happen? There is no water molecules, so they will not be able to carry out the H plus molecules. So you need to have moderate level of humidity maintained. 80 to 100% humidity is very good for this kind of membrane. Okay. And for polymeric membrane also, if we have polymeric membrane, if we have more than 100 degrees centigrade, this Nafion type of membrane loses its structure, this water channel they collapse. But if we go very high temperature, obviously the polymeric molecules they degrade at that much high temperature, they cannot sustain that much high temperature for this case. So we have to be careful about temperature, humidity, gas impurities, pressure variation, chemical exposure, and we have to check whether the longevity reduction is in a sustainable limit. So let us talk a little about how the carbon capture and hydrogen co-production can be achieved by this kind of composite membrane. So I was telling that we can impart some adsorbents for carbon dioxide into the membrane so that they can allow selectively hydrogen to pass through. Carbon dioxide, when it tries to pass through the membrane, they will be absorbed by these absorption processes. Okay. So the energy efficiency will be very high because we are also integrating two processes of carbon capture and hydrogen separation at the same time. We can have polymeric materials like PPAX, Matrimid. These are some commercial names. Inorganic membranes like palladium membrane based or MOF based or this kind of triple material for this kind of application. How do we know that our membrane is working properly? If we have carbon capture up to 85 to 90%, it is possible. So then we can use this membrane for our industrial application. But we have to be conscious that if our main membrane material is polymers, then we cannot operate more than 330 to more than 100 degrees centigrade operation. And if our main material is ceramic or inorganic, then we can go up to 400 to 800 degrees centigrade. What do I mean by main material? That is, if I have polymer as a main material, then the inorganic is infused in a polymeric matrix. So then we can go up to 100 degrees centigrade. If the inorganic is main material, then the nanoparticle or the polymeric particles, they are infused into the inorganic material up to 800 degrees centigrade. So we have to have a good trade-off between permeability and selectivity, and we have to have good membrane stability, and we need to have a hybrid system for this kind of material. I have already covered this information that we can have MOF, graphene or palladium alloy for composite membrane composition material, and we can also have mixed matrix membrane like zeolite, silica, etc. into the system. So for standardization, we can look for ISO 16100 2018 for safety standard. For standardization methods are on various aspects, not only on the purity level, but also on the safety level, the permeability and gas separation purposes. We have our DOE target, DOE or the Department of Energy. They have given a target that the membrane cost should be less than $200 per meter square, and hydrogen recovery more than 90%, and the durability of more than 5 years, so that we can have our composite membrane applicable in the industrial sector. So like this, there are some standards or the metrics that we should look for if we develop a new composite membrane and want to emphasize or extend it for industrial standard. So next coming to the safety consideration. So I was mentioning that hydrogen is very flammable, so we cannot allow absolutely no intermixing. We cannot allow any absolute intermixing between the hydrogen and other gases. So that's why if we have any exposure in the hydrogen, so it should be in the 4 to 75% range. If it is mixed hydrogen in the air, it is flammable. It will catch fire. So we have to be very careful about the hydrogen leakage. There should not be any defect in your membrane. There should not be any cracking in your membrane during the operation, so that you can be absolutely sure about there is no leakage happening inside this membrane. In this case, palladium membrane has stood the test of time. Pressure handling, membrane can be in such a way that it can handle up to 30 bar of pressure. Okay, 30 bar is a very high pressure limit, but why we have this thing in mind that it should be if there is a very momental variation in the pressure, in that any accumulation or coagulation or anything is there inside the membrane, it should not leak, it should not break. So that's why it should be able to handle 30 bar of pressure. Thermal stability for ceramic membranes, they should be at least stable in their TG value should be very high, so that it can be stable at 300 to 600 degrees centigrade. It should not lose its mass at sulfur and CO concentration, and these are the standard regulations for the safety consideration for this case. Now let us see if there are any industries which benefited by application for membranes in the energy sector. So now there is one product called PRISM membranes. They use membranes to recover hydrogen from refinery of gas. They have got hydrogen of 90% plus efficiency. They have got 30% energy savings by improvement over PSA method. There is shale and Evonik Separfan technology. They use it for biohydrogen production. It provides more than 98% purity, which is very considerably very high in this technology. We have high-gear hydrogen generation system, which employs palladium-based membrane for on-site hydrogen purification. We have IT-empowered electrolyzer with PM membrane used for green hydrogen production. We have DOE supporting the ammonia cracking method, which gives you very high purity standards. So there are different types of membranes that are offered in this scenario. Okay. Next, I am showing in this slide that how the membrane assisted technologies how they are performing compared to other technologies. Like say, if we have only PSA is an important tool for absorption-based gas separation system, which is pressure swing absorption. We can see that in all the technologies are sufficiently developed to give you almost 100% purity level, but energy consumption in membrane separation it becomes very low. Okay, compared to 2 to 5 for PSA and for electrochemical separation 50 to 55 kilowatt-hour per kg of hydrogen produced. So that way membrane separation, if you are assisting using membrane for this separation, it will give you very high energy efficiency. You can operate, you can vary it at different temperature. You do not have very strict pressure requirement or strict range, narrow range of operating pressure, and the cost is also very low. If we compare it, especially with metal hydride separation or electrochemical separation, the cost is because of the material cost only, capex cost, we have very low amount of cost separation. So what are the emerging trends? So what should we look forward to for our more widespread application of this technology? We should have more advanced membrane materials for which the researches are going on. We should have electrochemical method, hybrid method applied with this membrane separation, size-based selective transport. We can have cryogenic separation also, so that we can have cryogenic separation is what we are using these in a very low temperature. So we are liquefying our hydrogen. So that if we can use the liquefying efficiency, that only will enhance the overall process efficiency of when it is assisted by membrane. There is a very high shift towards the AI process. So if we know that from the AI analysis, if we know that which combination deals with the best operating condition, gives you the best efficiency, then we can identify the particular operating conditions for the maximization of the efficiency for our site. We have a huge market growth. So if we can show this, or if we can establish this markers for our performance of the membranes, you can have a very high growth rate of the market. In fact, EU is targeting 40 gigawatt hour electrolysis by 2030. Even our Indian government has taken up some efficient mission that like natural green hydrogen mission, so that we can use or we can focus more on this membrane based technology, hydrogen production technology for this section. So we should focus more on the AI, more on hybrid, and we should have scalable application. So now, why this scalability is important? Now, membrane in general is a very scalable technology. So it can be very highly, very easily, not very easily, there is established technology which can aid you to go from lab scale to industrial scale. But not everything goes proportionally. So if you have a 10 times more membrane area, you are not guaranteed to get a 10 times more lifespan. You are not guaranteed to get a few more properties. So what is the particular flux you are going to get? What is the particular permeability you are going to get? That is a research, or that is a physics based system. We need to have more focus onto this, so that we can be more knowledgeable about how to go for the small scale from the lab scale towards the industrial scale. So that's why also we have to be more careful about the techno-economic analysis. If we are not giving any cost-effective solution, it is bound to fail. You cannot have a very widespread application. So that is all that I had to talk about different aspects of membranes for hydrogen generation. What are the take-home messages? That it is very important. Membranes play a very role from conventional to latest technologies. There are different types of membranes. We learned about polymeric membranes, their specific properties, metallic, ceramic, and composite membranes. And we learned about the membrane technologies, how they work in different processes like membrane reactor, PEM, WGS, and SMR. We learned about their challenges and where the research focus lies in. We have learned about some industrial applications, future trends. We have learned about their standardization method, the safety standards, regulation, and initiatives by the government. So that's what we talked about. And so I am happy to answer your question now if you have any question. Thank you. So any question on the audience side? So if there is no question, so there will be a short break of 5 minutes, and then we'll proceed to the next session. Thank you.
Check.
Thank you. Thank you so much. So I had it was not, I had to focus on all the aspects. So slowly I will in the other sessions, so I'll focus mostly on the different other aspects of the storage and application.
The experimentation. Explain this process.
Yes.
Now we have the height here, no?
Yeah, we did not get any height in that session.
Okay.
So
Now we have a
you can have an interaction, or you can proceed for tutorial session. Okay, we can have a, so that's why I do. Yeah.
try to introduce the membrane processes for your family. In this section, we introduce all of membrane processes, and we'll first speak about the membrane configuration and the membrane models. Membranes can be fabricated as a flat sheet or as a tubular. Okay, we can prepare the membranes as a plate form or as a tubulars. If we reduce the tubular diameter to lower than millimeter size, we have hollow fibers. Hollow fibers is similar to the tubular membrane, but the diameter of these tubes is very small, and by this reducing the tubular diameter, we increase the surface area of the membranes in a specific volume. For flat sheet membranes, we have two modules. After preparation of the membranes for increasing the stability during the test and for increasing the surface to the volume, we change the membranes to the module. And in this slide, I want to introduce these modules. For flat sheet membranes, we have two modules. One is plate and frame, and another is spiral wound. For tubular membranes, we have also tubular modules that we have a big tube that can contain many number of the tubular modules together, or we can produce many tubes in one ceramic membrane. As shown in this slides, you see we have a structure that have many number of the plates. This is plate, these are plates, and this metal structure is frame. We say plate and frame. In a frame, in one frame, we have 20 plates. For fabrication of plate, we have this polymeric structure, you see, like as this. And in the left and the right side of the plate, we attach a membrane sheets with adhesive. You see, in the right, when we have this plate, in the right, left, and the left side, we have the membranes, and this membranes is immersed membrane, and for driving force, we used vacuum suction. In the next presentation, I say that we have direct pressure and vacuum pressure. In this style of modules, we have a suction pumps, and we have a vacuum pressure that apply for this tube. You see, this tube is connected to the big tube, and this tube connect a tube, permeate tubes connected to the vacuum pump. Therefore, as I said, in a vacuum, most applied pressure is 1 atmosphere. Therefore, this module is suitable for microfiltration and ultrafiltration. We have not reverse osmosis plate and frame modules. This is suitable and mostly used in membrane bioreactors. This frameworks used in membrane bioreactors for separation of microorganisms from activated sludge and increase of MLSS of the microorganism bass. Very good models from fouling view, because we can purge air or oxygen on the surface of these models, and cleaning of these models is very easy. With a sponge, we can clean these membranes for remove of the microorganism and other dirty. But the surface area the volume is low, because the flat sheet membranes is not a spiral, is not changed and directly used. The model preparation is simple, is suitable for MBR system, and the cleaning is easy. You see, this is the immersed in the activated sludge for treatment of wastewater. There are different structure for plate and frame. Was designed is stacked plate and frame. As you see, for this one, you see this is a plate, this plate, and between two plates, we have a free space. Together, huh? And between the plates, you see the feet come and go from the plate, and this module is rotary. When we have this rotary during of this central pipe, this rotary causes the reducing of the fouling, like as aggregation, and this agitation reduce the fouling and low need to the cleaning of this membrane. You see, the feed comes, and every passed permeate collected in this central tube. You see permeate, and after the finishing of this road, the concentrate goes out from the membrane models. There are other designs that I have not time to discuss. Second model is tubular model. Tubular model, we say that diameter of more than 3 millimeters, or more than 3 millimeters, and mostly used in industrial microfiltration, can be fabricated from polymeric, and can be fabricated from ceramic ones. You see this ceramic tubular modules. These tubular modules mostly used for separation of particles, and most used in clarification of fruit juice. For example, we have a pulp in orange juice, and we want to clarify the orange juice. In this case, we must separate this pulp from the orange juice or apple juice. And in this case, this module is used because the pulp is big, have a 2 millimeter, 3 millimeter in length or in diameter. We cannot use spiral wound. In spiral wound, the spacer between the membranes is very low. I showed the video. And when we have the pulps and particle, this particle can block the entrance to the module. Therefore, every place that we have a big particle, such as concentration of polymers. For example, in petrochemicals, one of the methods for production of PVC, polyvinyl chloride polymer, is suspended method. In suspended method, the PVC particle is produced, and for separation of the water from these suspended solids, use the tubular membrane. In the final lecture, I will speak about case studies. In this case, I more discussion. Generally, this tubular membrane is MF membranes. The cleaning is easy, this method, but the surface area is low, and the fouling can be controlled with increasing of the velocity and cross-flow speed. The third module, and the famous one, is spiral wound membrane modules, mostly used in NF, RO, gas separation, some MF, some UF. And for producing of this spiral wound, we use flat sheet membrane. With a wounding of a flat sheet membranes around a central tube, we change the flat sheet to a tubular modules. Okay, this is spiral modules with different diameter. Usually 8-inch. This is 8-inch. This is 4-inch. With the increasing of the diameter of the modules, the area of the membrane is increases. We have a central perforated tube that permeates, collect in the center of a tubes, you see. And between the membrane sheets, we have a feed spacer and permeate spacer. We want to have a distance for passing of permeate and feed from two sheets. Therefore, with using of the spacer, you see, this is a spacer, we distance between two sheets for easy passing of the feeds. We have videos, please play the video. In this video, we show that we how produce the spiral wound models from flat sheet membranes. We first prepare an envelope, and after round and wound about the tubes. Exit and play the videos. There are many videos in YouTube. This is pressure vessels.
To treat wastewater after the ultrafiltration process.
And inside of these pressure vessels, we have a module. This is a prepared flat sheet membrane.
A polyester fabric
For
support
RO
base,
membrane, we have a three-layer, non-woven layer, polysulfone layer, and polyamide layer. The thickness of polyamide is very low,
that removes nutrients,
200 nanometer.
bacteria, and viruses
The
from
selective
water.
layer is polyamide. For modulation, we first
Membrane flat sheet is
prepare
combined
an
with a sheet of
envelope,
feed
and this
channel
is a
spacer.
feed
This
channel
provides
spacer
turbulence and creates space between the membrane sheets
for
the
passing
feed
of the
water.
feed.
A sheet of permeate
This
spacer
one is
added
the
to the membrane
permeate
sheets
spacer.
and feed channel spacer.
Permeate spacer,
enables the
membrane,
final
feed
recycled
spacer,
water product, or
membrane,
permeate,
permeate
to
spacer.
flow evenly across the
Series,
entire membrane surface, even under high pressure. The back of the
see,
membrane is completely sealed to the edges
We
of
use
the permeate
adhesive
spacer.
for
The membrane sheets are
closing
glued along
all
each
of the
the three
membrane, and
exposed sides,
open side
rolled
is
around the
connected
core
to
tube.
the central tube.
Feed
When feed pass,
brain.
it
Water
penetrate,
passes through the membrane
permeate
surface
to
into
the entrance of envelope. and the
Permeate.
spiral wound and reach to the central
This water
tubes.
is the final product, or permeate. There are 7 spiral wound
You
elements
see,
loaded
in the
one
pressure vessel, for
Once the end
increasing
adapter
of
is connected to the
recovery,
last element
I
and the
say
pressure vessel
each
is
module
sealed,
have recovery
feed water can be
10 or
introduced.
15%.
Feed water is
For
pumped at high
increasing
pressure
of
into the
recovery
vessel.
in each
As it
pressure
travels,
vessel,
small
we have
molecules
4,
like water
5 or
pass through the
6
membrane,
modules.
while larger particles such as salt, bacteria and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water.
We have a feed entrance divided to
At St.
2
Mary's, there are
streams,
6
1
reverse
permeate
osmosis
and
treatment
1
trains, each
concentrate.
with 3 stages.
You see
This
here
design produces
the
highest amount
membrane in 3 steps. I speak about the stage in the next slide. You see stage 1, stage 2, and stage 3. For increasing of the recovery, we can use in membranes in 2 or 3 parallel steps. That means, for example, the concentrate of stage 1 can go to as a feed in the second stage. Or the permeate of stage 2 can be go as a feed of stage 3 for increasing water quality and recovery.
through stage 3, where the last percent of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St. Mary's. The remaining concentrate contains so much salt. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant, where it is
Play other
treated and
video.
released into the ocean.
Is finished. To hydronautics. This is similar to the first video.
To create a
Hydronautics is a membrane production factory.
membrane using hydronautics
This is also similar, show that how to repair the
brick support base
membrane
coated
module.
with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water.
This bright layer is the active layer,
Semi-permeable polyamide
and another layer is only supporting.
polymeric material, few thousand
Show the chemistry of the
angstroms thick.
this layer. For fabrication of RO membranes, we use interfacial polymerization that I will discuss tomorrow about this. And when these monomers connect together, we have some pores. The water can easily pass from these pores, but the hydrated ions, sodium or chloride, cannot pass.
The combination of these 3 layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane.
All of permeate goes to the
Membrane and feed channel
central
spacer are
tube.
then combined with a sheet of permeate spacer, which provides open flow channels for the permeate
Usually for
flow
8-inch modules, we have 24 envelopes.
Sleeves are glued along each of the 3 exposed sides. And then rolled around the core tube.
This is anti-telescope, and for pressure resistance, we have a fiberglass layer, about 3 millimeter, 4 millimeter of the fiberglass coating
Contacting the
for
front
pressure
of
stability.
the membrane. Clean water or permeate
This is feed spacer,
the membrane surface
and
channel,
between the 2 membrane is
the
permeate
center
spacer.
of the element
This
and is
anti-telescope.
collected into the core tube. Hydronautic spiral wound elements can then be loaded into pressure vessels.
Modules go to the
Elements to comply
pressure
with
vessels.
design specifications. Once the end adapter is connected to the last element and the pressure vessel,
concentrate of the first module go to the second module.
The feed water that does not permeate
and the permeate collect in the central tube. This is the permeate, and this red is concentrate.
The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel, producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed.
For brackish water, recovery is about 70 to 90%. And play the third video. Before modulation, we must, we must prepare the membranes, and we will discuss tomorrow. But I want to show that we first prepare these membranes, and next began to modulation. For reverse osmosis module fabrication, we need 14 instruments, 14 equipments that I showed in the slides. Therefore, the production of the spiral wound is expensive because we need many devices for production of different sections of the modules. This is a phase inversion method. You see, we have a polymeric solution like honey. You see, like it's honey, viscosity is similar to honey, and also the color. This is the film applicator. We can adjust with this the thickness of the layer, and the fabric began go from the bottom of this casting knife, doctor knife, and coat 200 or 150 micrometer of the polymer solution on the surface of the fabric, and directly go to the non-solvent. And when go to the non-solvent, the polymer, the liquid polymer solution changes to the solid one. And we say that phase inversion or phase separation occurred. Production of the membrane spiral wounds is high technology and need to control all of the process. The process is simple, but controlling the conditions is very hard. Measure the thickness of the membrane. Okay, I will tomorrow discuss about this fabrication. Go to slides. Okay. You see the production of this spiral wound, but we need many equipments for fabrication. When we speak about the spacer thickness, this usually is 750 micrometers. That means the feed channels have the height of this. Therefore, I said that spiral wound is not suitable for particles separation because the pulp can be block the entrance of the feed to the spiral wound. Therefore, before spiral wound, we need to pre-treatment for removal of particles. Before the spiral wound modules, we need to separate particles, usually use cartridge filter for removal of a solid. Permeate spacer thickness, you see this amount, and total membrane thickness after the total thickness with non-woven polysulfone and polyimide layer is about 150 micrometer. Usually the non-woven thickness, this one, and the polysulfone thickness, this one. That sum of this is this number. For fabrication of spiral wound modules, we need 14 equipment. One device for production of central pipe. We have a injection molding device for production of the central pipe. After preparation of the central pipe, we need equipment for perforating and producing of the pores in this central pipe. We need a device for production of anti-telescope and production of the O-rings for black O-rings and other machines. Therefore, I want to say that the production of the membrane modules is very expensive. Therefore, the price of the 1RO modules with 8-inch is about $700. Need to glowing device, trimming device, and fiberglass coating. All of need expensive instruments. The fourth modules is hollow fiber. Hollow fiber membranes have ID less than 1.5 millimeter. So I said that the tubular membrane have 3 millimeter, higher than 3 millimeter. Hollow fiber membrane is lower than 1.5. There is another categorization as capillary membrane. Capillary membrane between the hollow fiber membrane and tubular membrane, and the diameter is between 1.5 to 3 millimeter, but not usual. We have some capillary membrane, but not usual. Most of hollow fiber membranes have this diameter. You see that the human hand can be thousands of the hollow fibers. And the most properties of this hollow fiber membrane is that very high surface. And when we have a high surface, the productivity of the membrane will be increased. But one problem is that the stability of these fibers when fabricated from polymer is low. We cannot apply high pressure. In high pressure, these fibers can be tear and destroyed. Therefore, the surface area is high, but we cannot apply high pressure. Also, the washing and cleaning of the hollow fiber membranes is hard. In this slide, we compared the tubular, spiral wound, and hollow fiber modules together. A specific surface area, you see, meter square to meter cubic. Hollow fiber is very high surface area. You see, hollow fiber 15 times more than a spiral wound, and spiral wound 3 times more than the tubular. The surface area is high, but the flux of hollow fiber membranes is low. The flux is low because we cannot apply high pressure. We cannot, the surface area is high, but the flux is low. Therefore, when we introduce new concept, productivity, our production, that is the flux and surface area, we see that generally hollow fiber membranes have high productivity. But I say that hollow fiber membranes only used as a low pressure gas separation, microfiltration, and ultrafiltration membrane. Hollow fiber membranes cannot produce for RO. 50 years ago, some companies fabricated reverse osmosis hollow fiber membrane, produce hollow fiber membrane and coat polyamide layer on the polyamide, and fabricated a factory in Kuwait country. But after 2 years, all of the membranes destroyed and forced to change the hollow fiber RO membranes with spiral wound membranes. Therefore, in 15 years ago, hollow fiber RO membranes was fabricated, but because no stable, today not produced. When we check the cleaning, I say that the tubular membranes very easily cleaning and very easily replacement and no plugging, very small plugging. But hollow fiber membranes have a very high plugging, replacement is impossible, and the cleaning is very hard. We write not possible, possible. In some cases possible, in some cases not possible. But generally, the cleaning of the hollow fiber membranes is very hard. Therefore, as a conclusion, when we have a low pressure, low flux, the hollow fiber modules is the best choice. But for high pressure, we use spiral wound modules. And when we have particles in the feed, we try to use tubular membranes. As we show in the video, we have a different configuration and staging in the use of the modules and pressure vessels. In the first design, we have 3 parallel module or pressure vessel, and if a module have independent behavior, independent product, and in the final, for example, concentrate of all 3 mixed together and produce water mixed together. And we have one stage. We have different modules, but all have a similar fit and have a similar permeate and concentrate. Okay? With this, the parallel. But in the second configuration, for increasing of the recovery, I said that we have a usual recovery of 60, 70 in reverse osmosis. For increasing of recovery, we can the first step, concentration, go as a feed step in the second. When we see water, our feed, enter, and divide to 2 streams. One stream is permeate and independent, but the second stream that is concentrated, our brine, for more recovery, go to the second step. And also the second step concentration go to the third step. This is the series membrane, and this is for increasing recovery. For example, in this case, we have a brackish water modules. In this case, we can see water modules, and in this we can membrane distillation modules. The membranes types can be changed, but we want to increase the productivity and recovery. And in this case, we will have very concentrated solutes with high concentration of salts, and we must treat this brine for separation of salt. Usually, sedimentation is used for this purpose. In this second design, that named as Christmas tree, you see we can use both the permeate and brine of the first step go to the second step. When we use the brine, we use the permeate for second steps, the aim is increase of the purity. I show here. When we have a membrane, permeate, go to the second step, permeate, not concentrate. The aim is the high pure water. High pure water. For example, here we have this. When we go to the here we have this ppm, but we need this one. When we go the permeate of the first step to the second step, the aim is production of the high pure and low solid. But in this case, when we go the concentrate to the second step, the quality of the product water is similar, no change. But the recovery increases. In this case, the aim is increase of recovery. In this case, we want to increase the purity of the product. In the Christmas tree, we want to both them, both increase the recovery and both increase the purity. There are many different staging and configuration. Every company that fabricates the modules, such as hydronautics, such as FilmTech, have their software. And in software, you can select different design, different modules, and have 5 steps. And in step to step, you design, and based on your water quality and the concentration of feed, you can reach to different recovery. And if your design is not true, your data is not true, you cannot go to the second or third step. In software, you must type and insert true data. If your data have a rank, the software can predict and go that, for example, the concentration of anions and cations is not equal. We know that the charge of the solution is neutralized. When we have 10 cations, we must have 10 anions. We measure the feed concentration, and if the concentration of anions and cations is not equal, the software is not accepted and say that your measurement is not true, and others. The software is very good for this staging and configuration. Is there any question about module? If need, I can more discuss. This is tutorial, and in tutorial we must discuss if you want. No question? Okay. I go to second step. In the second step, I want to introduce the membrane processes. As we have 22 membrane process, and we have more than that, maybe 30. But this process is relatively famous. The first processes is the many famous microfiltration, ultrafiltration, nanofiltration, and the reverse osmosis. And the first lecture I discussed about that the separation is based on the pore size, and the MF have the big size, and the NF have the low pore size. This is a typical large-scale MF, UF, and NF or RO plant. We have a feed tank, usually. We have many pumps based on the volume of the factory, that these pumps apply pressure to the feed, and feed go to the pressure vessels and pass from the modules, divide to stream, one concentrate and one permeate. Based on the process, concentrate can be product or permeate can be product. In UF, usually concentrate is product. For fouling reduction and control of conditions, usually we add additive to the feed. You see a little tank with a little small pump that dosing some additives to the entrance of pumps. These additives reduce the membrane fouling. Mostly is the pH adjustment. We control of pH, we can reduce the fouling. We can change the protein charge, membrane charge, all be used. And go to the modules and divide into stream. This is a usual UF, NF, and MF process. About the control process of this unit, so we see that we have a pump, we have a pressure indicator transmitter before and after membranes. We must apply delta P as a driving force, and we must measure all of the parameters. We measure the pressure, flow, and temperature for controlling of the conditions. For applying the pressure and controlling of the recovery, we have a closed loop that measures the flow and control this valve for controlling of the recovery and pressure. With closing of this valve, we reduce the flux and increase the pressure. This is a typical control system. You see microfiltration and ultrafiltration in dairy industry. In dairy industry, microfiltration used for separation of skim from the milk and sterilization of the milk. Microfiltration can be separate the bacteria from the milk. You see that all of the pump, this is pump, and this is pressure vessel, all of the tubes is stainless steel. Because for sterilization, every day use the chlorine agent and the oxidation agent, most application from different fields. For example, oil-water separation. With UF, we can separate oil from water or water from oil. If we have a hydrophilic membranes, we can separate water from oil. And if we have hydrophobic, we can separate oil from water based on the concentration of oil and water. Separation of whey, whey is the product of cheese. After producing of cheese, we have a liquid that have a soluble proteins. For separation of soluble proteins, we can use the UF membranes, and we have a UF cheese. We have a UF cheese. The name of the cheese is the UF cheese. That means UF used for the concentration of this cheese. Concentration of biological macromolecules, such as membrane bioreactor. We separate microorganisms from the sludge. For recovery of the paint from electrocoating, concentration of heat-sensitive proteins. We can, you know that the proteins, when heat, denaturalization. The proteins is denaturalized. And the denaturalization change the properties of protein. Therefore, when we use the membrane, in membrane separation, we do not need heat, and therefore the proteins is safely separated. Concentration of gelatin, in production of gelatin, we must separate the water. As you see, in most cases, we want to separate water from a solution, and the product is concentrated, not water. In the gelatin, our product is gelatin concentrated solution, not gelatin water. Separation of enzymes. Enzymes is a protein. Pulp mill. In the pulp mill, we use the tubular membrane and other processes. There are many, many applications for UF membrane. Another application is gas separation. In gas separation is a high technology with the polymeric or ceramic membranes. We can separate two similar gas. For example, nitrogen and oxygen have a similar size, but we can separate them from together by membranes. In lecture 9, I will speak about gas separation. Therefore, I pass this slide. This is a commercial hollow fiber gas separation membranes that I opened this. This is used for hydrogen separation. This is hydrogen separation, hollow fiber membranes. One of problem of gas separation membrane is aging. In aging, the polymer from flexible state changes to the brittle state. When I contact with these hollow fibers, the membranes is powdered, very, very brittle, and cannot touch this membrane and destroy the membrane. Very, very application I will discuss in lecture 9. Other application is a membrane bioreactor. In the membrane bioreactor, you now, in biological reactors, the microorganisms eat the carbon-based material as a feed and destroy the organic matter. Microorganisms with eating of the chemical oxygen demand, COD, remove the COD and BOD. And after this treatment, of microorganisms eat this food, and the population is increased. And we must separate the extra microorganisms. The traditional method is use of the precipitation tank or sedimentation tank. And because the hydrophilic nature of microorganisms, the sedimentation is very slow and therefore need a very big tank for sedimentation. And almost 1/3 of the treatment plants is related to the sedimentation of the microorganisms. But when we use the membranes for separation of microorganisms, we no need to the sedimentation tank, and the size of the treatment unit is mostly reduces, and the quality of the water is also high. In sedimentation tank, we have not complete and good separation, but in membrane bioreactor, membrane can be separate efficiently the microorganisms. This is an experimental setup in lab scale that used hollow fiber membranes for separation of the microorganisms. Any question about discuss? Huh? No discuss. Huh? Please discuss. Another membrane process is pervaporation. Pervaporation. Pervaporation is used for separation of the liquid. For separation of low amounts of impurity from the solvent. The famous example is the separation of water from ethanol. The famous example I show, this you see, you know, after biological change of the sugar to the ethanol, by distillation, we can separate ethanol from water. And when we boiling the mixture of ethanol and water, ethanol have low boiling point and vaporize and go to the gas phase, and with condensation, we can separate alcohol or ethanol from water. But in this point, in this percent, 96% of the alcohol and 4% of the water, we reach to the azeotrope point. In azeotrope point, the difference boiling point between water and alcohol is removed. And when we boil this solution, the composition of the alcohol water in gas is similar to the liquid phase, and we cannot separate 4% of water from ethanol. For resolving this problem, in industry 30 years ago, add benzene or toluene to this 96% and redistillation. By addition of benzene or toluene, the azeotrope destroyed, and with redistillation, the absolute ethanol, 100% ethanol is produced. That is very expensive. If you want to buy 1 liter of 96 ethanol, it's maybe 50 rupiah. But if you want 1 liter of absolute ethanol, it's 500 rupiah. 10 times is expensive because the separation of this 4% is very important. And in many organic reactions in the petrochemicals, we need a pure ethanol. The water is poison, is toxic for the reaction. For separation of this 4%, the famous technology now in the world is using of the pervaporation membrane. In pervaporation membrane, we have a non-porous membrane. Here we have no porous. Membrane is dense. We have a feed, and here is the air. But for increasing driving force, we have here vacuum. We have a little vacuum that causes the driving force for penetrating and permeation of the ethanol from this membrane. Therefore, in PV process, we separate mixture of liquid. The membrane is non-porous, and membrane can be both hydrophilic or hydrophobic. If we want separate water from solvent, for example, we have a hexane and have a 1% water. We want to remove 1% water from hexane. We used hydrophilic membranes that water pass and hexane do not pass because hexane is organic. But reverse, if we have a 1% hexane in 90% water, we use hydrophobic PV membrane that hexane pass and water not pass. Therefore, in PV, based on the separation molecule, we can use hydrophilic or hydrophobic membrane. Usually, the vapor can permeate. Liquid, some ethanol or hexane also can diffuse. But we know the diffusion rate of gases is very high than liquid. Therefore, for helping to increasing diffusion coefficient, we heat the feed. But this heating is not very high. For ethanol water in azeotropic, we heat about 50, 60 centigrade, not reaching to boiling. We want to reduce the energy consumption. With increasing of the heat, mostly 50, ethanol, some of ethanol can change to the vapor, and the vapor pass from the membrane. And this pervaporation, permeation vapor is produced from mixing of permeability and vaporization, pervaporation. Therefore, the vapor can pass from the non-porous membrane. Here is the partially vacuum, the vacuum level. And after reaching of the vapor here, we need to condensation. For condensation, we condense and reduce the temperature for changing of the gas to liquid. Therefore, you see in the permeate, we have a condensate. This is heater, this is refrigerator. Reduce the temperature. This is a schematic of the pervaporation membrane. The mechanism of separation is solution diffusion because we have not pores. The membrane is non-porous. The ethanol adsorb on the PV membrane and diffuse. There are many applications. Removal of water from organic solvent, dewatering process is dehydration or dewatering, separation of the ethanol alcohol from fermentation baths for ethanol, propanol, and very, very different. And there are many factories that produce the pervaporation modules, but pervaporation modules is expensive relatively, 6 times of the RO membranes, half price. You see, the pervaporation membranes can separate isomers from together. Isomers, cis trans, have the similar molecular weight, and separation of them with UF and F is not possible. But with pervaporation, we can separate isomers from together. You know, the Brazil is the most producing ethanol in the world. And in Brazil, most of cars use ethanol instead of benzene, or mix of benzene with ethanol. You can use 50 ethanol and 50 benzene or diesel in your car. And in the Brazil, the first plant of pervaporation about 50 years ago is constructed. Excuse me. This is a Sulzer company. Sulzer is the famous production of PV modules, and that this design is hybrid system that for ethanol or isopropanol separation, this percent produced by distillation, and for complete removal, usually used the pervaporation process. The membrane is located here. Any question about PV?
Organic solid.
No, this is have some. Repeat.
Yeah. Are you able to hear? Yeah. I mean, like, we generally use dimethyl formamide for the synthesis of MOF. Yeah. Generally, we, face the problem of separating this DMF from some organic substrate that we, like, if it is in the DMF solvent, we can't separate the DMF because of its high temperature. Yes. And also, we face the problem of DMF and water. We can't separate that because it will form azeotrope at 100 degrees Celsius itself, where water has to, evaporate. So we can't do through normal distillation process. Is that possible with your membrane technology, the DMF separation?
You want to remove DMF or water?
DMF and waters, we want to separate DMF itself because of its high temperature.
How many DMF? The amount of DMF, how many? 10%, 5%?
So generally, like, I encounter 5% of DMF. 95%.
You want to separate DMF from your water?
Yes.
In lab scale?
Yes.
In lab scale, you cannot use PV, so you need the heater, you need the vacuum pump and condensation, and you must buy the PV. But the DMF boiling point
153 degrees Celsius. 153 degrees Celsius.
Yes, but the water is 100.
Yeah, but it will not be possible. I tried through that
you cannot separate them.
Yes, sir.
You can use zeolites. You can hydrophobic zeolites can absorb the DMF, or organic pollutant from water. When you can use you prepare a hydrophobic zeolite column and pass your solution, and the DMF can absorb on the zeolite and water pass. And can you reduce the DMF? You can ask from organic chemistry students. Mostly they remove the organic from the water for impurification of our products.
Okay.
You can use zeolite. But PV is, can you use PV in industry, but in lab scale, it's very expensive for you. When we want to use hydrophilic polymers for PV, we usually use polyvinyl alcohol. Polyvinyl alcohol is a hydrophilic per evaporation polymer, and for reducing of the swelling, usually cross-link the PVA for separation of water. For separation of DMF, you must use PVDF or PTFE membranes, non-porous membranes, for separation. The other process is dialysis. In the MF, UF, NF, RO, most of gas separation and pervaporation, the driving force was pressure difference, delta P. In dialysis membrane, the driving force is concentration difference, delta C. Here, we have a delta C. This membrane, similar the ultrafiltration membrane. We can use ultrafiltration membrane as a dialysis membrane, similar pores. But in UF, we apply pressure for feed side, but in this dialysis, we have not pressure. The pressure of the feed and permeate side is similar, okay? No pressure. But we have a difference in concentration, and we have a difference in size of the molecules, okay? You see here, for example, we have a pore size. Usually this pore size for dialysis membrane is 20 nanometer. In 20 nanometer, you see that the big molecules cannot pass. If we apply pressure also, they cannot pass. But we want to separate a selective molecules from the feed. You see here, this blue with thick sign have not passed. The size cannot be from the size, but they cannot pass. Why? Because we have these molecules in permeate side. In the MFUF, in the permeate size, we have only air, weather, no solution. But in dialysis, in the permeate size, we have a flow of permeate. We have a receiver liquid. In the both side, feed side and permeate side, we have a fluid. This feed flow, and this is the receiver or dialysate. When we have these molecules or ions in the permeate size, we have not delta C, because the concentration of this blue is similar to the permeate side. Therefore, these blue ones do not permeate. But in this red, we have not here the red ones, and we have a delta C, and those can pass from the membranes. Therefore, in dialysis membranes, we have two mechanisms. Pore size effect, big molecules cannot pass. The small ones, if we have a different concentration driving force, it will be passed. If we have not, they cannot pass. The most and famous application of the dialysis is hemodialysis that acts as a kidney for separation of impurity of the blood and the urea, lysozyme, and other dangerous molecules from the water can be separated. But we do not sugar of the blood separate. Okay, if the sugar of the blood is reduced, we have a healthy problematic. Therefore, we add sugar. This is sugar, and the sugar of the blood cannot pass because no difference in sugar concentration or NaCl. We know the blood is salty. We use the salty solution, and the salt of the blood no pass, but the urea can pass and separate from the blood. Also, there is the other application, for example, recovery of sodium hydroxide or recovery of the expensive metals, such as gold from the streams. We can use this hemodialysis or dialysis process. The membranes in dialysis is porous. The size is similar to the UF membrane, usually fabricated from polyethyl sulfone, polysulfone, and others. This is the models of the dialysis and hemodialysis. And most of hemodialysis membranes is hollow fiber because we want to increase the surface and reduce the time of hemodialysis. The hemodialysis when we illness, the hemodialysis illness is need 2 times in a week go to the hospital and hemodialysis for 2 hours. If we use the flat sheet membranes instead of hollow fiber membranes, the time of hemodialysis increased from 2 hours to 6 hours. Therefore, with use of hollow fiber modules, we reduce the hemodialysis time. Any question about dialysis? A relatively new membrane process is imprinted membranes. Imprinted membranes show in this slide. From the first time, we want, and we know that we want prepare a membrane for separation of a specific ions or a specific molecules. Okay, this shows that when we, from the first time, we prepare an imprint, only for this molecule, and other molecules cannot pass from the membrane. Therefore, we say imprinted membrane. For example, show that after preparation of these membranes pores suitable for this key, not for this one. Therefore, these membranes act very, very sensitive and prepared from polymers. And these polymers mostly used in sensors for detection of some impurities in the water. It's very, very sensitive. And we can use these polymers for the fabrication of imprinted membranes. Based on the application, this imprinted membrane can be categorized to ion imprinted and molecular imprinted. Membranes, that means ion imprinted separate a specific ion, such as nickel, cobalt, heavy metals, and the molecular separate organic matters from water. For preparation of this ion imprinted or molecular imprinted membranes, if we have a template molecule, we want to pass only this molecule from the membrane. Therefore, we prepare a specific site that only match with this molecule. And other molecule cannot absorb in this free location and cannot pass. Okay? Mostly can be used as an adsorption membrane. Mostly can absorb a specific metal such as gold, silver, palladium, platinum. And after adsorption, we can separate the membrane and go to the release solution. And with change of pH, usually these adsorbed molecules can be desorbed, and we can separate the specific molecules. For preparation of this structure, we must use network polymers. Network polymers, that means between the chain of polymers, we must cross-link. Because with the change of temperature, the imprint should be stable. And for stable configuration, we use 3D dimensional polymers. Therefore, we have a monomer, target, and we have a cross-linker. We mix monomer, cross-linker, solvent, and target together and prepare a film. And after film, we go to the membranes, to the oven, and with heating or UV radiation, complete the polymerization, and the obtained films can act as a membrane. This is high technology membranes. This shows that we can use one monomers, two monomers, or three monomers. But necessary we have a cross-linker. Cross-linker have two functional group for polymerization that connect the top chain to the bottom chain, and we have a restrict and very hard network. And the obtained the pores is special for this molecule. For example, with this method, we can separate trans from cis. Pervaporation also can separate, and imprinted membrane. In pervaporation, for separation of two isomers from together, we must have difference in boiling point in pervaporation. Because we must have a difference in boiling point, one isomer change to the vapor and pass the membrane. But in this membranes, we no need to the difference in boiling point, and the membrane's free space is based on the difference in structure. This membrane is suitable for this one and not suitable for this one. And we can separate two isomers or enantiomers from together. Any question about imprinted membrane?
So previously you mentioned about the isomer separation with respect to pervaporation. Their boiling point difference is required.
In pervaporation, we need the difference in boiling point between two isomers. But you no need. Separation based on structure. Another process of membrane is electrodialysis. In electrodialysis, we use both cation exchange membrane and anion exchange membrane in parallel. Okay? We have one anion, cation, anion, cation, anion, cation. Okay? And we want to separate salts and charged molecules from together. And the driving force is delta E, electrical charge. Therefore, we have an anode and cathode. Okay? And between this anode and cathode, we have usually 10 membranes. 5 is cation and 5 is anion. Anion, cation, anion, cation. And the distance between two membranes is about 1 millimeter. When you see electrodialysis, you see only two electrodes, two metals, with very compact. But in this area, in this 2 centimeters, we have 10 membranes, and distance between the membranes is 1 millimeter. Why is near? Because we reduce the electrical resistance. We reduce the ohm. And as you see, in anion membrane, only pass the anion. And anion membrane pass anion, cation membrane pass cation. Okay? This is a sodium exchange membrane. This is a color exchange membrane. As you see, with we have a 1 feet, and this 1 feet enter between all of the membranes, but the product is divided to stream, concentrate, and diluted. You see here, color go to the right, sodium go to the left. And here, we have a purified water or desalinated water. But in the right or in the left of this area, we have a concentrated, because the color cannot pass from the cation and the sodium cannot pass from the anion exchange membrane. And the driving force, you see, the sodium wants to go to the left because the negative charge here, all of the cations go to the left, and all of the anions go to the right because they're positive. But therefore, we have a one rod with concentrate, and one rod have a desalinated. Driving force is the electrical and this similar that. For this exchange, we need some functional groups in the membrane body. For sodium passaging, we need sulfonation group, sulfonation negative group, absorb the sodium. And for color passing, we need the ammonium positive groups on the membrane. Electrodialysis is good for low desalination processes, usually used after RO. RO reduce the high concentration to low concentration, and for low concentration use, we can use this for produce low saline. And we cannot produce demineralized water, DI water, because for conductivity, we need the ions. We cannot complete removal of the salts, because for conductivity between cathode and anode, we need to the ions. Okay. Usually this process now used in desalination of protein solution. In the fabrication of the in the fabrication of different type of protein lysozyme. For desalination of the protein solution, usually use the electrodialysis, very low use in the water treatment and reducing the salts. If used for groundwater, is used for brackish water, not seawater. This is the I discussed. This is the experimental device for testing of the electrodialysis membrane of ion exchange membranes. All is non-porous membrane, like as this. The Nafion membranes, Phelemion, Aquavion, all of these similar membranes and not porous. This is the industrial units of the EDR. Another application of membranes and exchange membranes is in the fuel cell that Professor Raka discussed and will also discuss. We use the protein exchange membrane in the fuel cell for passing of the proton and going to the react with oxygen for production of H2O. Also, exchange membranes is used in color-alkali industries. In color-alkali industries, we want to pass sodium from this anode house to the cathode house for production of the chlorine gas and hydrogen gas and hydroxyl solution that usually use the exchange membrane, sodium exchange membrane. Before membranes, usually use the diaphragm separator, and before the diaphragm separator, usually use the mercury method. The mercury method is very dangerous, and today use the membranes, such as this, for the production of the color gas, hydrogen gas, and hydroxide from NaCl solution. In this industry, saturated brine, NaCl solution come and electrolyze to chlorine, hydrogen gas, and hydroxyl for production of NaOH as an alkaline. Another question. No question about exchange membrane. Liquid membrane also is used mostly for recovery of expensive metals. Liquid membranes similar to the liquid extraction. In liquid extraction, we have a ligand that's a specific complex with a metals and transfer that metal from water phase to organic phase. And in this membranes, we have usually carrier agent for separation. Have two types, mostly emulsion liquid membrane and supported liquid membrane. In supported liquid membrane, we usually have a ceramic membrane with big pore size that the pores of the ceramic membranes filled with the liquid. This liquid usually is oil-based, usually is paraffin that have a complex agent and can absorb from the feed water to the receiving phase. We have a source phase or feed phase, and some molecules can contact to the carrier and go to the receiving phase. And in this case, we can have passive or active transport. In passive, we say high energy, high potential, go to the low potential. But in some cases, we have an active transport, as discussed in the lecture 1. This is show also the different cells of the liquid membranes. You see in this case that we have a U tube. In the bottom, we have usually water. This is the water phase. And this phase is organic phase. Organic, usually on top of the water. And we have a micelles, our acceptor phase. These micelles can selectively absorb selected molecules from the organic phase to water phase or reverse, from water phase to liquid phase. Have different configuration for the cells for separation of these molecules. Usually we have a feed and receiver phase, and mostly used for recovery of expensive metals. Another membrane process is membrane distillation, or MD. MD is used for desalination, most application for desalination, and usually used after RO for treatment of concentration of RO. RO, when the concentration of the salt go very high, when reach the concentration to 100,000 ppm. In this concentration, RO cannot work because the osmotic pressure is very high, and this concentration caused to the saturation of many compounds, and this saturation can deposit on the membrane surface and cause to the fouling and scaling. I will next discuss. calcium carbonate, calcium sulfate can be deposited in this concentration and the membrane will be destroyed. In this case, we can use membrane distillation for more treatment of the saline solution, because in this case, we have no many concentration and we have no pressure, delta P, because in this membrane type, the driving force is temperature difference. We have a porous membrane, we have a porous, and we want that vapor pass, not liquid. We want to vapor pass, such as per-evaporation. We want vapor pass from the porous membrane. In the per-evaporation, we have non-porous. In the MD, we have porous membrane. Both PV and MD, vapor will pass. We want only vapor pass, not liquid pass. Therefore, the membranes should be super hydrophobic. Super hydrophobic. The contact angle should be higher than 120. Because when the water enter to the pores will be blocked and the membrane do not work. The pores should be free, should be open for passing of the vapor. Therefore, water should not pass from the pores of MD membrane. Therefore, in this case, we use hydrophobic materials such as PTFE, PVDF, polypropylene, and other hydrophobic polymers, such polyimides also used, such polyether ether ketone can be used, and others. Therefore, in this membrane type, the driving force is delta T. We heat the feed. In this process, we heat the water solution, usually 80 centigrade, but we do not reach to the boiling point. And as I say, the most energy used in the phase change. When we have a boiling, in the boiling point, we need many energy. But we do not reach to the boiling point. We increase temperature to 70, 80, and in 80 centigrades, some vapor is produced and pass from the membrane, hydrophobic porous membrane, and condense in the permeate size. Based on condensation method, in the permeate size, we have different types of MD. We have a direct contact membrane distillation. In the direct contact, we have a cold stream on the permeate side, okay, such as dialysis. In dialysis, we have a flow in the permeate side. In MD, we also have a flow in the permeate side. In the direct contact, the cold stream directly contact on the membrane bottom layer. In the first configuration, and this method is not good because the permeate solution, such as feed solution, can wet the membrane and fill the pores. Okay, we do not like the pores fill with the water. In direct contact, we have a second stream that the possibility of the going to the membrane pores is increased. In the second category, we have a vacuum. We have a not stream in the permeate side, and every permeated vapor sucked to the condenser and changed to the liquid. Therefore, in this area, we have a vacuum on the permeate side, but this vacuum should be very low. We do not like have a delta P. Okay, we do not like. Therefore, we have a very, very low vacuum only for suction of the vapor. In the second design, in the third design, we have an air gap between the cold stream and the bottom of membrane. In the permeate side, we have an air gap that here we have a stainless steel metal. In the behind of the stainless steel metal, we have a cold water. Cold water reduces the temperature of the metal, and when vapor penetrates, diffuse from the membrane and go to the air gap area, when contact with the metal, condense and drops began to dropping. Okay? In this case, this space about 3 millimeter, 4 millimeter, and we have a metal barrier, stainless steel barrier, and we have a stream behind of this metal. In the last design, we have a sweeping gas. In this vacuum, we have a vacuum pump, but in this case, we have a sweeping gas, usually air or nitrogen, with low flow come from the bottom side, permeate side, and sweep every penetrated vapor, go to the condenser for condensation. The MD membranes can be flat sheet, can be hollow fiber, or can be spiral wound. We have a different module for these membranes. I discussed these slides. This is the lab scale vacuum membrane distillation. I say that we do not like the pores is filled with the liquid, and the pore size and the hydrophobicity of the membrane is very important. Usually 30 nanometer pore size is good, and super hydrophobic membranes, rough membranes, the surface roughness is very important. When we have a roughness membrane, the contact angle increases. Sweeping, we have an air or nitrogen sweep on the behind of the membrane. Any question about MD? No question? I will finish in 10 minutes. Okay. Other membrane process is membrane contactor. Membrane contactor can be used for degassing or gasification, like as at absorption column and desorption column. In, for example, natural gas have carbon dioxide and H2S, and these gases cause to the corrosion in the transferring tubes. Therefore, the natural gas companies separate the carbon dioxide and H2S from the methane with absorption column, that we have a amine solution that can absorb acidic gas. H2S and carbon dioxide is acidic gas, and amine is basic and can absorb this acidic gas. But in this case, we have a direct contact. And I said that the membrane process is indirect. In this process, the loss of the amine solution is very low, and the contact between gas as liquid increases. In the absorption column, we have a tray for increasing of the contact between gas and liquid for mass transfer. In this membrane contactor, we usually use hollow fiber membranes, and hollow fiber membranes have a very high surface and increase the contact between gas and the liquid. Yes, in the fit site, for example, in the out of the hollow fibers, we have amine solutions, and in the inside of the hollow fibers, we have a methane and carbon dioxide. And carbon dioxide can penetrate to the amine solutions and separate. Therefore, in a membrane contactor, we use hollow fiber for increasing contact area. We use porous membrane, and we use hydrophobic membranes. Because in hydrophobic, the water cannot penetrate to the pores. Okay? The membrane contactor membranes is similar to the membrane distillation. Membrane distillation and membrane contactor have similar membranes. And the final process is photocatalytic membrane reactors, that PMRs. PMRs is similar to the MBRs, membrane bioreactor. In membrane bioreactor, we mix biological treatment with membrane separation. In this case, we mix photocatalytic activity with membranes. Photocatalytic activity with membrane. Photocatalysts degrade the pollutants, organic pollutants, with using of catalyst and photon. Photon can be produced from UV lamp or solar or visible light. Okay? When the photon conduct to the catalyst surface, produce radicals, mostly hydroxyl radicals, and these hydroxyl radicals can degrade the organic pollutant. Usually, membrane is used for separation of catalysts after photocatalytic activity. Okay? Usually, membrane act as a separator of the catalyst from the slurry solution. And in some cases, we can deposit catalyst on the surface of a membrane. But this is the most used. We have a external membrane that you see the light goes to the production of the radicals on the catalyst. And after the photocatalytic is completed, for separation of the catalyst, we can use the membranes. These membranes can be external or can be immersed in the feed solution, such as this. This is an external and can be used immersed. And in immersed, we use the vacuum suction for separation. Mostly MF and UF membrane is used for separation of catalyst. And in some cases, we can immobilize photocatalyst in membrane surface, but with immobilization, the surface area of the catalyst is reduced and the efficiency of the process is reduced. Thank you. In the last speech, everybody is tired and sleepy.
So all the participants are requested to make use of this opportunity to interact.
I try to, in this section, introduce only the membranes, processes, and have more time for more discussion. I will try to discuss about this mechanism in the next lecture, but if you want more explanation, we can discuss face-to-face.
Yes. So apart from the topics also that we are discussing here in this topic, in case you have any question from another or related topic, you can personally approach us or use this opportunity to ask this question. So I encourage all of you to, because these offline seminars are attended or organized because of that, to enhance the connectivity between all of you with the expert lectures. So if we do not ask questions now, if we keep silent, so we are losing out. So please understand that and feel free to ask anything. So that is my suggestion to all of you in order to enhance the objectivity or successfulness of this course.
We can discuss about everything, not memory. we can transfer our experience in water treatment and gas separation to you. If you have questions that not related to membranes, but if your mind, you can ask.
Yes, yes. That will be great. Yes.
About liquid membranes.
Yes.
So commercially, are we using it?
Huh?
Anywhere liquid membranes? Because solid, that is well versed. But what about liquid membranes? How far is it?
You ask about application, huh?
Yes. Is it currently?
The application of the liquid membranes have some problems. The main problems is that the organic liquid that filled in the membrane matrix is not stable. After 1 month, littered to the feed, and after 1 month, we see that all of organic is finished. And this is the one problems in liquid, and therefore liquid membranes should be used in 2-3 days. And there are some plants in gold extraction that use this liquid extraction on the membrane surface for continuous separation. In the emulsion liquid membrane, the difference from the liquid extraction that our extraction is continuous. We have some plants that use the mixture of two organic phase and water phase, and after 10 minutes, let me to separate the phase and separate with the Buchner funnels. But in a liquid membrane, we have a continuous extraction. But another problem that some this liquid when go to the water phase have some dangerous environmental, because most of this extractant is toxic, and generally the environmental problems do not permit to more development of this process. But in the gold process, now the extraction and production use cyanides. And cyanides is very dangerous. And in this case, use of the liquid membranes from environmental view is suitable and used for extraction.
One more question regarding this gas separation. Whatever molecules you want to separate, they have similar molecular weight. So if I want to separate one molecule, so what about the selectivity? Generally, they reduce the selectivity. For example, similar molecular weights of like oxygen or nitrogen. These molecules, when you want to separate one molecule, other molecule also comes together. So which type of membrane separation this can be achieved?
Yes. In the gas separation, we have two kinds of membrane, porous and non-porous. Porous membranes is used in gas separation when the molecular size is very different. For example, separation of hydrogen from butan, pentan, very big pentan, hydrogen is little, and we can use porous membranes with mechanism of Knudsen diffusion for separation of this. But in the similar molecular weight, we have a solution diffusion mechanism and non-porous. In this case, we have two parameters, solubility and diffusivity. When we have a similar molecular size, the diffusivity is similar, but the solubility will be different. Based on the chemical structure of gas and chemical structure of the polymer, the solubility is different. One gas more soluble and other low soluble. Therefore, we have a difference in solubility. After solution, the diffusivity is no change. Therefore, in this case, we say this membrane and this gas separation is based on the solubility, not diffusivity. I will discuss about gas separation.
Thank you so much. Thank you all for joining in today's session. And we are very happy that we could organize today's lecture and that Professor Ratanpur has enlightened us with so many information about this specific topic. And so tomorrow our session will start again at 10 a.m. as per schedule that we have shared with all of you. So please join us tomorrow here in this room. Thank you for joining us today. Have a good day.
Thank you. Have a good day.
Fuel cells. So